Okay, welcome everyone to the third day of the conference. I don't think we have any announcements today, right? No. So we are all focused on an exciting day ahead of us, and we will start with Timo Weigand from Hamburg, who will tell us about infinity and finiteness in strings and geometry. Please go ahead.
Thank you very much. Good morning, everybody. Thanks for coming. And let me start with a big thank you to the organizers for making possible this event and the generous invitation. It's really great that we're all assembled here in this beautiful place, so many young people, and it's really exciting to be here. So thank you very much for doing this. So I'd like to talk about two different projects, one in physics, one more on the mathematics side, with these collaborators, in particular, in the Hamburg paper with Fabio Mantegazza, who's also here, PhD student from Hamburg, who presented some of this in the poster and who's also here to answer your questions and discuss more if you would like to hear more. And then a math paper with Antonella Grassi and further collaborators from mathematics. So as has been featured in this conference very prominently already, two important hallmarks of quantum gravity are, on the one hand, the appearance of infinite structures, so infinity of towers of gravitationally coupled particles far out at infinity in the moduli space. And on the other hand, boundedness, finiteness of the number of light gravitationally bounded degrees of freedom in the interior of the moduli space. And that these two are not in contradiction with each other is a consequence of duality, in particular the duality conjecture and the swamped distance conjecture and the emergent string conjecture assert that these infinitely many states far out define a new duality frame, be it one dimension higher in decompactification, be it a string frame in which then the remaining degrees of freedom are really finite. So in this talk, I'd like to try to understand these two important aspects of quantum gravity a bit more in two different contexts. In the first part, I'd like to take a closer look at the nature of these towers, not in flat space, but in ADS gravity. And in particular, I'll be focusing on partial or generalized recoupling limits as they appear, for example, in 4D n equal 2, or in principle also in 4D n equal 1. And in the second part of the talk, I'll then switch topics a little bit and focus on issues of finiteness and discuss bounds of the model Y group of elliptic vibrations as an example of these physics predictions for geometry. And I will discuss recent math proofs and also generalizations and going beyond what was known from the physics. So that's the roadmap, and let's see how far we get. In particular, in the spirit of this meeting, the first part of the talk will be more focusing on the string side, and the second part of the talk will be on the geometry. So, string towers in ADS gravity. The goal of this project is to understand better the analog in ADS of the types of limits that are well familiar in flat space by now, namely on the one hand decompactification limits and on the other hand weak coupling or emergent string limits. And in particular, the hallmark of the latter type of recoupling string limits in flat space is the appearance of a string tower. It's a fundamental string, so a string from which, in particular, the graviton arises as one of the excitations. And the tower arises parametrically at the Kaluza-Klein scale. That's the third important point. And the excitations are of exponential degeneracy at the mass levels, the well-known classical properties of fundamental string excitations. So if we'd like to understand the analog of this in ADS, things get complicated, but of course it is here where the holographic dictionary and holography can be very helpful. The infinite distance limits in ADS are dual to infinite distance limits on the dual conformal manifold on the moduli space of the conformal field theory. And indeed, these authors famously have translated the distance conjecture into a statement on the conformal field theory side, the CFT distance conjecture. In particular for CFTD with d bigger equal 3, the infinite distance loci are conjectured to be always weak coupling limits at which higher spin towers, so currents, conserved infinitely many higher spin currents arise. And this has been studied already in great detail in a number of wonderful papers. In particular, the overall weak coupling limits have been studied in great detail. I do not have time to do justice to these many results, but I trust that Irene, right after me, will discuss this in great detail, or maybe at least review bits and pieces of it, maybe not. If not, you have to ask her after. So the focus in this talk will be a little bit different. I'm going to focus on mixed weak coupling limits, and I'd like to make the comparison to the emergent string limits in flat space. So let's start very slow with things that are very well known. And first look at the easiest case of such limits in the context of ADS5 gravity. This would be a dual, of course, to n equal 4 superconformal field theories. And on the gravity side, the important thing to keep in mind, as we all know, is that there are now 3 length scales, namely first the 5-dimensional Planck scale, then the ADS scale, which is the same scale as also the Kaluza-Klein scale associated with the S5, because there's no scale separation in these models, and then the string scale. While on the dual CFT side, the parameters are the rank and then the one modulus, the one-dimensional direction on the conformal manifold, the Toft coupling or the gauge coupling. And the latter, the gauge coupling, of course, controls the ratio of the string scale to the ADS scale, or the string scale to the KK scale, and the ratio of, say, the KK scale or strings or ADS scale to the Planck scale is fixed by n, the rank of the gauge group, the number of these 3 branes. And from now on, we will keep n very large but fixed. And in this regime, as we all know, as long as the Toft coupling is very large, we are in the familiar regime of effective supergravity in ADS. The hierarchy in this case is such that the string scale, the type 2B string scale, is very much higher than the ADS scale, which is the same as the KK scale. And the towers that appear in this case are first the tower of a string of the type 2B string, which sits at the string scale. It's exponentially degenerated. And then there's in addition to this also a supergravity KK tower, which sits at the ADS scale or the KK scale. This is typically polynomially degenerated. These are the KK modes associated with the massless supergravity fields, which of course we also have. And about these states, one can dually think from the conformal field theory point of view in terms of dual operators. These operators have a certain conformal dimension and a spin, and the mass in terms of the ADS scale is then fixed by the holographic dictionary. Here is an example of the well-known dictionary for how to compute, for, in this case, bosonic fields of J not equal to 0, the corresponding mass. And importantly, the conformal dimension has two contributions, a tree-level one and then a quantum one. The quantum anomalous conformal dimension governs the mass in the dual regime as a function of the Toft coupling. Now, to take the infinite distance limit, which would be the analog of the weak string limit or the emergent string limit in flat space, we take the direction lambda to 0. And clearly, in this way, we enter the substringy regime. So the string scale wants to go below the KK scale or below the ADS scale. And then supergravity is not a good description. Rather, we better think of this in terms of a dual weakly coupled CFT. With this caveat in mind, I will nonetheless pretend that there is a notion of mass in ADS, and I will treat this dictionary mass as an effective mass, but keeping in mind that we are really in a substringy regime. What happens now is that as lambda goes to 0, the conformal anomaly vanishes, the anomalous dimension vanishes, and the conformal weight of the states is given by its tree-level value. And in particular, as one can see from here, indeed, powers of states can become light, namely essentially when the first term hits 0. This is the case when delta 0 becomes 2 plus j, j being the spin. And in this case, the mass of these states, of course, goes to 0. And these are the very well-known and well-studied higher spin towers. They come from operators of this type on the dual CFT side, which all derive from the building blocks of the n equal 4 vector multiplet. And this is precisely the pattern that is predicted by the CFT distance conjecture as studied in these papers. But importantly, if one wants to compare this to flat space, one should keep in mind that these states which become light in this way differ a little bit from the expectation from flat space, namely their degeneracy of increasing mass is not exponential, but rather polynomial, because these are representations of the Lorentz group of increasing spin, and these increase with J polynomially. So the situation that we have is that already for this well-studied and very well-known type of limits, we have some complications compared to flat space, namely the string tower, which at large lambda in the interior of moduli space is well above the KK scale, wants to become lighter and lighter and lighter. Some of these states, the higher spin states, in fact, do become light. So we get this higher spin tower. These are states of vanishing R charge. And indeed, this is the reason why their mass goes to 0 in terms not only of the Planck scale, but also of the ADS scale. While on the other hand, the majority of all the states from the string tower stay at the ADS scale or at the KK scale. So we have a remaining string tower of exponential degeneracy, but this does not become light. It becomes light only with respect to the Planck scale, but not with respect to the ADS scale. So the big bulk, the exponential bulk of the string, so to speak, gets stuck at the ADS scale. It doesn't get below because we enter the substringy regime, and quantum corrections from the worldsheet point of view stop these states from becoming really massless. Okay, so this is the well-known situation in N=4. And now we'd like to ask if this behavior is general or what else could happen in such limits. And in particular, I'll focus here on string theory and ADS5 times a further background that results in some N=2 supersymmetric theories. One can also generalize this to N=1. And in this case, in particular, the dual conformal field theory admits several directions, not just one. So we can consider more general recoupling limits. On the dual CFT side, the directions one can take are now at infinite distance those of vanishing gauge couplings. And clearly we can again take an overall free coupling limit. And again, this has been studied in particular in these papers. On top of that, one can also take a mixed limit. So one can take one or several of the couplings to 0, but keep the others in the bulk of moduli space. And this is what I'm going to look at in this talk. So we are interested in these mixed type of limits. And the take-home message is that in such limits, the nature of towers is a bit more complicated. Namely, in addition to all the towers that we discussed already that are inherited, so to speak, from the N=4 structure, there's a new phenomenon. Namely, one finds a new type of towers, extra states. These are interacting, so they are strongly coupled. They are not weakly coupled string towers, but they are strongly coupled and interacting. They sit at the ADS scale, and they are nonetheless related to the higher spin tower through supersymmetry. So the distance conjecture, the CFT distance conjecture, focuses on the appearance of the higher spin tower, and this is indeed something that is also characterizing these more general limits. But these extra states here are indirectly a consequence of these higher spin towers. They're related to them via representation theory. And this is indeed the key message, that in this strongly coupled situations where these extra strongly coupled but nonetheless protected states, which become light with respect to the Planck scale but not with respect to the ADS scale, appear, that the appearance of these states is a consequence already of representation theory. So more precisely, what's happening is that as we take the limit of one or several of the extra couplings to 0 while keeping others finite, that there's a certain BPS splitting of BPS multiplets happening. More precisely, in the bulk of the theory, we start with so-called long superconformal multiplets. So these are multiplets of the superconformal algebra, and long because they do not satisfy any shortening conditions or any BPS conditions. And these are typically labeled by the primaries in their multiplet. From then all the other states arise by acting with the generators of the algebra. And these are labeled by an SU2R symmetry for the N=2 and the U1R symmetry. Okay, and now I'd rather not move. until the danger is over. Very good. And the key point now is that as we take one of the gauge couplings to 0, what happens is that one or several of these multiplets can hit a meaning that the conformal weight of the associated primaries hits a particular value, this one or this one, at which now the multiplet decomposes into several shorter multiplets or BPS multiplets. This in that literature is known as recombination rules and has been studied in great detail from the SCFT point of view in these papers and others. And for example, if the multiplet hits both of these shortening conditions at the same time, then what happens is that it decomposes into 4 shorter multiplets or BPS multiplets. The notation is a bit awkward, but again, it's labeled, these multiplets are labeled by the SU2R symmetry and the spin of the primaries in these multiplets. So we have a splitting of long multiplets into short multiplets. That's what's going on. For example, and that's in particular the key player for us, we can consider the multiplet of vanishing SU2R charge and of vanishing U1R charge. Then in the interior of moduli space, this is just some long multiplet. As we dial one of the couplings to 0, this theory, this multiplet behaves in such a way that the conformal dimension approaches its free value up to an anomalous dimension, which goes to 0 precisely when we have set one of the couplings exactly to 0. And then what happens is that we have the splitting into 4 BPS multiplets in this case. And these will be exactly from which the types of towers then emerge. More precisely, this first multiplet is exactly the higher spin current, the higher spin multiplet, as predicted by the CFT distance conjecture. So this is a multiplet, if you look at the precise values of the dimensions, whose mass really goes to 0 with respect to the ADS scale. And this comes from the free sector of the SCFT. But by supersymmetry, there are also other types of multiplets related to this first higher spin tower. And in particular, the top multiplet here, this is the one that contains these extra states which are protected. Namely, these are states whose mass with respect to the ADS scale is not 0, because the conformal dimension is not such that this would be happening. However, nonetheless, the mass is protected. The mass is protected by supersymmetry. So these states are not arbitrarily heavy. They become lighter, but they don't make it until mass 0. They keep being stuck at the ADS scale. And interestingly, they are protected even though they are highly interacting states. And this is precisely this phenomenon that this extra tower appears. It appears from a tower of excitations which are somewhere at very high energies in the middle of moduli space. And then as we go to take one of the couplings to 0, along with the higher spin tower, which becomes light, also these extra states appear, and they are interacting, exponentially degenerated, and they are stuck at the ADS scale. So this is a general phenomenon, and it holds whenever this representation theory can be applied. Now one can look at this in examples, but this is really just to illustrate this. For instance, one can study the simplest case of a 4D n=2 ADS theory. This is dual to a 2-node theory of gauge group SUN with 2 bifundamental hypermultiplets. And in the interior of moduli space, both of these gauge couplings for n and for both factors of n would be non-zero. For example, we can go to the orbifold point where they're both the same. There the theory is very well known as ADS5 times S5 over Z2, where in particular also the R charges, the SU2R and the U1R, have a very clear geometric interpretation. And now what I can do, just to see it in an example, is keep one of the couplings fixed, say for the left node, and take another coupling for the right node to 0, and as I hit 0, my quiver has split into a quiver of S of superconformal QCD on the left side, and then a free vector multiplet. So this is precisely the type of generalized limits, and all these limits which start from such quivers in general will take this form. And one can now already look at the type of the part of the spectrum of this superconformal QCD part here of the part of the theory, which is still at strong coupling, which is inherited from the orbifold theory. And it was noted already in this paper in 2009 that the part of the spectrum that is inherited includes only R symmetry singlets. So they are singlets under the SU2R. The SU2R is associated with the extra S3 in the geometry. This means that the states that are inherited from the orbifold do not see the extra S3. So there's no KK tower associated with this extra S3. And in that sense, these authors stressed that this should be viewed as sort of non-criticality in the sense that these modes do not propagate in the full dimensions. But nonetheless, the states come from the original type 2B string, in particular the type 2B string, which gives rise to the graviton. And now the extra states that are advocated, one can try to analyze explicitly, for example, by looking at the type of Witten index in these theories. One can compare the index for the SQCD factor from what is inherited from the orbifold point, and one finds a mismatch. And this mismatch is precisely due to the appearance of these extra BPS states due to the splitting or recombination rules. And one can look at this index in more detail and indeed confirm that these extra states are exponentially degenerated. And one can go further and try to identify the multiplets explicitly. This is in particular what we did in the paper then to show that these states are really there and that indeed their mass sits at the ADS scale because they all carry R symmetry. So this was the message for the first part. Now, in the remaining few minutes, I'd like to give a quick update on the topic of boundedness theorems for model Y groups on Calabi-Yau threefolds. So why is this interesting from a physics point of view? Because the subsector of abelian gauge symmetries in F theory is in one-to-one map with the free part of the group of sections of elliptic vibrations. Those of us who have been in this meeting for a longer period know this very well because this was discussed at great detail some time ago in the F-theory literature for obvious phenomenological reasons. But indeed, it is striking that this oftentimes viewed as somewhat mysterious concept of sections, of rational sections of elliptic vibrations, has such an easy and nice and down-to-earth interpretation from a physics point of view. And in particular, from a mathematics point of view, it was for a long time not known what types of bounds exist on the number of possible sections which an elliptic vibration could have. So from an arithmetic point of view, this is an interesting question that mathematicians actually care about. And of course, the same question is, what is the maximum number of abelian gauge symmetries that we could have in F theory? We may or may not care about it, but at least I care about it because it's an example of a question of boundedness. As we heard in this conference, as we heard also yesterday in David's talk, this is an important question to see what type of bounds exist on the light degrees of freedom in quantum gravity. So this is the reason why I'm interested in this. And indeed, physics motivated bounds for the number of abelian gauge symmetries, which then translate into bounds on the number of sections on these elliptic vibrations. So making use of this idea of probe strings, as introduced in this paper by Kim, Shiu, and Vafa, one can indeed derive bounds on the number of abelian gauge symmetries that one can have in such F-theory constructions, bounds in 6 dimensions, and also bounds for Calabi-Yau fourfolds, even though in the latter case, universal bounds from physics were not known. So if you talk to your favorite mathematician and you're proud and happy and tell them, look, we've got some idea from physics for what the bounds could be, they smile, but they are relatively unimpressed because first of all, these are all just physics results. So nothing has been proven from their point of view. And then of course, they immediately ask, can we find universal bounds also for fourfolds? Can we extend beyond fourfolds? General Calabi-Yau n-fold, and can we also extend beyond Calabi-Yau? And this is where this project started. And indeed, the answer to all these questions is yes, we can to a certain degree. So in the paper, we prove 2 theorems. The first is that if we consider an elliptic vibration, Calabi-Yau threefold, including all the bad things that you can ever be worried about, like Q factorial terminal singularities and whatnot, then the number of rational sections can never extend 28. That's a theorem, and it can be extended beyond certain Calabi-Yau cases, and it also includes those situations where the existence of a bound is not yet guaranteed by rational boundedness theorems from of the type studied by Svaldi and others. And then second, this reasoning can be extended. We give a universal bound for the number of sections for elliptic Calabi-Yau fourfolds. It's 38, under the assumption that the base B is smooth, which from a physics point of view is the case that we care about. And clearly there's a pattern here. The pattern is that for general n-folds, the rank would be 10n minus 2. And I don't have time to go into the details, but the idea is first to bound the number of sections of the fourfold or of the general n-fold by the number of sections of a suitably embedded surface, which is easier to handle, and then find universal bounds on the types of surfaces that can appear. And here one has to make use of certain properties of birational geometry in order to find universal bounds, and this is how they occur. For Calabi-Yau threefolds, the bases are essentially P1 fibrations or smooth Del-Pezzo surfaces that can occur. And similar results also hold for Calabi-Yau fourfolds. In particular, the hardest part was here to show that indeed 38 is the highest number that you can get. And I should say that this is really a formalization of all the ideas from the physics. So after the dust has settled, the mathematicians agreed that the physics already essentially knew all this, except of course this acrobatics about finding the universal bounds, which is really a geometric question. Okay, let me conclude. In the first part of the talk, I looked at partial decoupling limits in ADS. In particular, in the most general decoupling limits with some of the gauge nodes remaining finitely coupled, we identify a protected, strongly coupled, but exponential ADS tower, and it's related to the higher spin tower, but in a non-trivial way via representation theory. And these extra states that appear there are indeed related to the original type 2B string excitations. So even though one can view it in this sense as a non-critical string, because it may not see all of the dimensions as the propagating string, it's what I would call a gravitational, a fundamental string. This is the string from which the graviton arises. And this can also be generalized to situations with n=1 supersymmetry, and this is work in progress. And second, we reported on geometric proofs for bounds on module Y ranks, and in particular made a conjecture to any dimension. And finally, let me make a shameless advertisement. In summer, we have a school on geometry and physics, on algebra, geometry, quantum field theory, and strings. And you are, of course, all very welcome to come there and enjoy the interplay of geometry and physics and geometry and strings even more. Thank you very much.
Thank you very much, Timo. So we have time for questions.
Hi, Timo. Thanks for the super nice talk. So I'm curious, it might be a matter of terminology, but I'm curious what would you say if I ask, like, you think that we need to modify the emergent string conjecture or rephrase it, or I don't know, like refine it to account these non-critical, like subcritical strings?
Right. So thank you. Yeah, I think it's a matter of terminology. So probably one shouldn't say a critical string arises, but more a fundamental string arises. I think the important thing is that the excitations that you see are related to really the string from which the graviton comes. So it's not what one would call a non-critical. I mean, there are two types of non-critical strings, right? There are the non-critical strings which are critical from the Welshi point of view, but they don't have propagate in 10 dimensions. These I would still count as the ones that are very similar to the flat space result. And then there are the non-critical field theory strings, and these are not what seems to be appearing. So in that sense, I think it's as close to the flat space result as it can get. But taking into account all these complications that already arise in ADS 5 times S5, the curvature and these mass corrections and so on. So the splitting into polynomial and exponential, that's something that simply has to do with the ADS structure. So then it's a matter of terminology, but I think that's at least how we view it.
Thank you. So I had a question for the second part. For the finiteness results, can you extend them to genus 1 vibrations or multi-section geometries? Or
Well, in those cases, the answer is 0 because we do not have any sections.
but can you put bounds on, let's say, the order of multi-sections and of this type?
Very good. Probably yes. So we did not look at this. So what I mean, there are. So these are supposed to be mirror dual, presumably to the discrete the discrete part of the model Y group, right? There were these papers by Clevers and others 10 years ago that showed that at least for the torus, there's a mirror duality between the number of multi-sections and the discrete part of the model Y group. And the discrete part of the model Y group is also bounded by this. I didn't go into the details here, but we also bound them. And I'd also like to advocate this paper where with completely different methods, the discrete part was also bounded. So if this mirror symmetry holds, this would also put a bound on those, but this is something to investigate more. Thanks, good idea.
Hi, so I want to add. So for the first part, because we know that there are some partial result on the integrability for the Engels-2 queer gauge theory. So is there any interesting tower from the long multiplets?
A tower from the long well, I think the long multiplets will generically be very massive. So they are there, absolutely, but they are not protected. So they give rise to this whole mess up here, which is which continues to be really very massive. So probably from integrability techniques, you may know what the states are, but they will be very, very heavy. So if you now take an additional limit and also make the second, so this would be for this case where, we have taken one gauge coupling to 0, and now we have the remaining gauge coupling. So if you take this one also to 0, then these states, number 5, will come down and will be sitting then at the KK scale here. While these states here will decay, will become irrelevant, at least in the large N sector.
Yes, another day. Okay.
So in view of time, let's thank Timo again. And we save other questions for the coffee break. Okay, so for the second talk of this morning, we have Irene Valenzuela from Madrid and CERN, who will tell us about limits in warpland and CFTs. Please go ahead.
Thank you so much. Okay, so of course, first of all, thank you to the organizers for the invitation and putting together this conference. I think it's very nice. I'm enjoying all the different talks. And thanks everyone for being here already the third day, so that's good. So I'm going to talk mainly about two things, mainly one. So the most part of the talk I will talk about this work in collaboration with Nacho Ruiz and Salvatore Raucci about going on a trip to the warpland. So we are going to study the Kaluza-Klein spectrum in warp compactification. You will see why. And then at the end, I will give you some updates on these infinite distance limits in which we get new strings in area CFT, following what Timo talked about just before. Okay, so let's go to the first part. So it's clearly a long-standing problem to understand the Kaluza-Klein spectrum in string compactifications, especially when we have warping. With this, I mean when we have some compactification, which is not just a direct product, so you have some warp factor that depends on internal dimensions. And clearly, I mean, there have been many, many works many years. I mean, it's a very old topic. Let me just refer some recent works of the past 4 years only in the context of string compactifications. There are many different reasons why you could be interested in this topic, because you want to get information about the gap or some cosmological applications. I mean, many different things. Our motivation came from the swampland distance conjecture. As you have heard in several talks, no? We have this central idea in the swampland, which I also think is one of the most universal features that we observe in the string theory, which is that we have these towers of states arising at infinite distance and decaying exponentially in Planck units. And there has been many works quantifying this, identifying the towers, no? As you have seen. I think there has been very nice progress. In particular, I think one of the biggest developments is that this alpha, this constant, no, on the exponential rate, was originally some arbitrary constant, but with all the work of many people, I think right now we understand much better what can it be. And it comes from identifying these towers, okay? Because the point is that the value of this exponential rate depends on the microscopic nature of the tower. And so far, it seems that in at least in flat space compactifications, the tower, as you have heard, always corresponds in some dual frame to a Kaluza-Klein tower or a string tower, okay, coming like oscillator modes from a critical or fundamental string. And that seems to fix these values of the exponential rates in terms of the dimension of the space-time and how many dimensions you compactify, which suggests these bounds on the exponential rate, okay? So the lower bound is given by the tower of the string, coming from the string, and the upper bound from the compactifying one dimension. And if you decompactify more, typically you are in between, okay? So you might have seen this in several talks, but the point is that, I mean, this value of the Kaluza-Klein tower is valid when you have some homogeneous decompactification in which the warping gets diluted, okay? It's not important. Asymptotically, you recover the result of that you would have without warping. So the question we had is, okay, how does it modify? No? What happens if now I have warping? How does it change this exponential rate? And in particular, can it violate these bounds? Okay. So our goal was, to take a look at the Kaluza-Klein spectrum in warp compactifications and check, especially, how well motivated are these bounds. I mean, they have also been proposed independently, but I mean, if we want to quantify this conjecture, we really need to understand if there is, if this is just a matter of the lamppost, no? Or if there is something fundamental behind this lower and upper bound. Especially the lower bound, I think, is very important because it gives you how heavy the tower can be, no? What is the slower rate at which it decays? So if you want to get upper bounds on the scalar field range that you can travel, you need to put a lower bound on this exponential rate. Otherwise, if it can be parametrically small, this is meaningless, okay? So that's very important. And let me mention, I'm gonna refer to this bound as the sharpen bound because it was proposed first in this paper, which was called like the sharpen distance conjecture, okay? But it's this lower bound proposed for the exponential rate. Okay, very good. So, first of all, before going into it, so what we would expect, okay? Do we expect that the warping decreases or increases the exponential rate? Okay, so let me give an expectation just based on one example that we know the answer, okay, to see how it goes, which is the type 1 prime, okay? So this is the Polchinski-Witten solution. So I have 208, some D8 variants, and I have a Minkowski warp solution, warp compactification in 9 dimensions, okay? It has a modular space in 9 dimensions, but there is a non-trivial profile for the dilaton and for the warping, no? In between, no? In this interval. So already in this paper a few years ago, we computed the Kaluza-Klein spectrum in this particular example, and we found that the exponential rate decreases compared to the expectation without warping, okay? So it's this value is smaller than the famous formula, okay? So it seems that indeed the exponential rate can decrease, which means that this lower bound, a priori, can risks to be violated. No, the question is, could we have enough warping, like strong enough warping, such that we get Kaluza-Klein tower that would have an even smaller value of this exponential rate? Maybe the string tower also changes, I don't know, but the question is, how universal is this bound? Okay, so that's what we try to answer in this paper. So let me give you what we found. So for concreteness, I mean, of course, this is a very general question, so we need to make it concrete to give an answer. So we focus on these Minkowski work compactifications, like this type 1 prime. Okay, so we still have some flat space, but there is a non-trivial profile for the scalars. And then we are going to study Kaluza-Klein spectrum for scalar modes, okay, the scalar Laplacian in highly warped limits. So with this, I mean that when you have the moderate space, there are many limits you can take. We focus on those that the warping does not get diluted asymptotically, so the ones that have a chance to change the exponential rate. And let me distinguish between two cases. One is codimension 1 in the sense that the sources, like the O8 planes, okay, giving rise to the warping are codimension 1, so the warping depends only on one internal dimension or bigger codimension. So let's start with the codimension 1. So the setup is simple. I mean, we want to generalize this Polchinski-Witten solution, so we're gonna take like some general Lagrangian with some Einstein term, scalars, and some scalar potential, compactify one dimension and get, plus sources, and compactify one dimension and get a Minkowski warp solution. Okay, so this includes the type 1 prime example I gave you before. It's just that, as I said, there is one direction in this type 1 prime, which is this highly warped limit in which you decompactify to massive type 2A. Okay, so it's like as if, I mean, it's equivalent to say that I start with massive type 2A, so the potential is just the Roma's mass. I compactify with the Orienti-force and the D8s, and that gives me rise to this Polchinski-Witten solution in 9 dimensions. Okay, so what we are gonna do is, rather than assuming, so before we had the result for this, for the Roma's mass, so it's this particular value of the, I mean, in Einstein frame, depends on the dilaton, and we have this particular exponential rate in the potential. We are gonna compute the Kaluza-Klein spectrum in general for any gamma, okay, any exponential rate in the potential. So that includes the Polchinski-Witten solution as one of the cases, but it also includes many other, comes from non-SUSY models, dynamical cobordisms, I don't know, different examples, okay? Well, no, that one is different because there is no the warping. It's just like the dilaton doesn't have the, I mean, it's like, it's not, I mean, it's like I'm going precisely like if you want Horava-Witten is related in the same model space, but I'm going to directions which are not highly warp limit. Okay, so I'm gonna skip the details. I mean, in order to compute this exponential rate, you need to know the metric in the modular space. You need to know to solve the Laplacian for the Kaluza-Klein modes. We do it for large KK momentum. Okay, so we get some universal result. And then we have to solve the equation of motion to get these internal profiles in general. Okay, so we do it in general for any value of this potential. There are different families of solutions you can get, but all of them share this result for the exponential rate. Okay, so the main result is that in general, starting with any of these exponential potentials at any sources, such that it cancels and you get Minkowski, the exponential rate at large KK momentum is given by this, which indeed is the result without warping that gets modified by this gamma, which tells you know what's the, it's related to the source of the warping, no, this potential and the sources. Good. So indeed, this is always smaller than the result without warping, okay? But if you just allow me any potential, like any type of source with any exponential rate, it can get as small as you want. Okay. Now, you can ask, okay, to what extent this bound is satisfied? Well, remarkably, this lower bound that we had for the tower, for the exponential rate of the tower, works only if this gamma of the potential, okay, the exponential rate of the potential in higher dimensions, is bigger than this, which, this is the serpent bound, is precisely the condition of no acceleration if the potential was positive. Okay, so this is the Strong-de-Sitter conjecture of TCC. So here, I mean, notice that this is in different dimensions. Okay, so it's like the exponential rate of the tower in lower dimensions, for instance, in type 1 prime in 90, in comparison to the exponential rate of the potential in higher dimensions, in 1 dimension more. Okay, so there's a nice correlation between the two, which I don't know why it happened. But indeed, it seems that this bound, it also works for Kaluza-Klein towers only if the potential is steep enough originally. Okay. And this is the condition for no acceleration. The potential is positive, but let me remark that this works both for positive or negative potential. Okay, you still have always this correlation between these two bounds. So this is nice. I mean, if we could find, I mean, if we have a more fundamental explanation for one of them, then we can relate and use it for the other. Okay, there is a one-to-one correspondence. Okay, so that was the KK tower, and the paper we also discussed how the Planck scale changes, the string scale, and so on. Maybe in view of time, maybe let me skip this. I mean, you can just compare the different exponential rates; they all get reduced. And maybe make a comment about the higher codimension case. So what I told you was the general result for codimension 1. If you have, the warping depends on more internal dimensions, so the localized sources have higher codimension. You can still aim to give an answer. I mean, we still, the result that we have for the Kaluza-Klein in lower dimensional Planck units still works. We also do the dimensional reduction, but the problem is that, I mean, to solve in general the equation of motion, I mean, it's impossible. I mean, you have to make some choice. So here we only consider, rather than having like a completely arbitrary potential and so on, right? We consider now sources that we know, so concrete values like they coming from the deep brains and S5 or planes and so on. And then the point is that we didn't find any limit which is highly warped, in the sense that even if there is warping, the warping does not get diluted asymptotically, so that the asymptotic exponential rate of the KK tower seems to be always the one associated without warping. Okay, it would be nice to have a more general, more systematic study, but yeah, so far only in codimension 1. I mean, it's a matter of the codimension, no? Because the internal profile depends on the codimension. So only in codimension 1 it grows fast enough that it really changes the Kaluza-Klein spectrum asymptotically. Okay, so yeah, so what we have seen so far. So warping defects indeed can decrease the exponential rate, the asymptotic value of the exponential rate even, if we are in codimension 1. But if we want to violate this bound, then we need to get already like some acceleration in higher dimensions. So to be fair, I mean, I don't have any top-down example of this asymptotic potential, no, this running potential that accelerates yet. So far, it seems that this lower bound for the tower survives. If we could find an example of that, then we would need to modify, no, this bound. So this bound survives the trip to the warpland, and then the remaining time, I wanted to try to challenge this even more. No, so I mean, I really think we need to try to go to all the exotic corners, no, to see whether we can change these exponential rates. Flat space, it seems they are fine. So the question is, okay, can we challenge this in ADS? No, because so far, even if I added warping, there is something common in all these cases, which is that I was considering Minkowski compactifications. So the remaining time, let me just quickly give you some update on this, what happens in ADS. Okay. So let's consider infinite distance limits in moduli spaces, but now we have an ADS space-time. So now I'm very grateful that Timo already reviewed very nicely what happens the distance conjecture in ADS CFT. So the point is that this moduli space maps to the conformal manifold. And the point is that many of these infinite distance limits, they move us away from the regime of supergravity. So we need to consider the limits in the CFT. So we need to do the dictionary, okay? Consider the CFT perspective. We can translate this distance conjecture to the CFT. This is the CFT distance conjecture, in which we should have this infinite tower of operators saturating the unitarity bound at every infinite distance limit measured by the Samorgikov metric in the conformal manifold. Okay, so in the same way that in flat space, I mean, it has been, very nice systematic works, different classifying all the different limits that we have in large classes of compactification and so on. We can try to do the same in CFTs. We can take CFTs that are known and understand what are the possible limits that we have, what are the possible towers, what are the exponential rates. I mean, the same story, okay? And in the talk like 2 years ago in this conference, what I did is precisely to focus on this topic and give you some first steps towards a classification of infinite distance limits in 4-dimensional superconformal field theories, okay, that would map to limits in moduli spaces of ADS5. So the point is that all the limits, all these infinite distance limits that are known in CFTs, they always correspond to weak coupling limits from the CFT perspective. So there's a gauge coupling that goes to 0, you get a free sector, which is at infinite distance, and that's, since it's a free sector, it means that you are gonna have a higher spin symmetry, which means that you have an infinite tower of higher spin operators, and you can go through the details to show that they decay exponentially, as Timo reviewed. Okay, so the exponential rate in this case, you can also compute it purely from the CFT perspective of these towers. It's given by the square root of the ratio of the central charge over the gauge group that gets free, the dimension of the gauge group that gets free. This is from the ADS perspective, and whenever we have a large n limit. And since we are talking about higher spin fields, it suggests that these towers come from some bulk string that is becoming weakly coupled and tensionless in Planck units. And the question is, okay, can we classify what are the possible strings that we have? And if there is anything different than what we found in flat space. Okay, so in flat space, we always, whenever it's about a string, it's always the critical type to be like, or heterotic, no? Like the fundamental string. And it always has this exponential rate, which is 1 over square root of d-2. So how does that change? So in this, in a paper with Jose, what we did was also to take, to start the classification somehow. So the beginning is to consider just gauge factors, gauge groups that have only one simple gauge factor. And large n, I'm gonna focus on large n. Even if this works without, even if you don't have a large n limit, you still have the towers. Let's focus on large n so I can think what is the dual string tower, okay, in the ADS. So I want to have a weakly coupled ADS dual. So for simple gauge factors, all the Lagrangian for the CFT were classified in this paper, so you can take them. And what we found is that they get divided in 3 universality classes that have 3 different values of the exponential rate for the towers, okay? And these classes were mixing different levels of supersymmetry, different values of the gauge groups. So, as I explained, we did in this paper, spent 2 years ago, we had these 3 possible values. We checked that in all these cases, you can find some Hagedorn-like density of states. There is a Hagedorn temperature, which actually is different in each of the 3 cases, which suggested that there were 3 different types of tensionless strings in the bulk in this mini landscape of CFTs. One of them was appearing in all the theories that were Einstein, and it was just the fundamental type 2B string, and there were 2 more, okay? Which at that moment, we had some idea this was some non-critical string, but the third one, we had no idea what it was, okay? So the update I wanted to give you is that now we understand these 3 strings, okay? We have explicitly confirmed these previous expectations that they correspond to 3 different tensionless string limits, identify the string by constructing the dual brim picture for each of these CFTs, okay? Including those that are non-Einstein, okay? So even if they have a large n, they don't have a large K. And this is what is a, well, ongoing work with Jose Calderón Infante and Ángel Uranga that we expect finish soon. So let me just give you the answer, and with this I finish the talk. So we have these three classes, okay? So they said we construct the brain dual for all of them. The ones in yellow were already known, and to the best of our knowledge, if I didn't make any mistake in the tables, the ones in white were not known before. Okay, so these are all new. So these two, so let's start with the first table. The first table were those that are actually holographic, so they correspond to some Einstein gravity. So here, of course, most of them were already known. No? What is the brain picture, no? That gives you this CFT. You can always, we are gonna, just for consistency, in all the cases, I'm just gonna give you the type 2A brain picture, okay, like some Hanani-Witten construction. So in all these cases, you have some D4 brains on a circle with different orientifores, orbifores, brains, and so on. They all have this exponential rate for the higher spin tower, and indeed the weak coupling, the overall weak coupling limit is just the critical string, okay, the type 2B string. In the second case, we also construct all these brain pictures. The first one was known. This is the super QCD. I should have added, sorry, here also the recent work by Timo that he talked about. So this is what they focus on. So already in this paper of Gaia Pomoni Rastelli, they give a very nice interpolating model to provide the bulk dual of this super QCD example, which is non-Einstein. So what we do is the same for all the other cases, okay? So, and in all the cases, as you can see in the picture, they are characterized by approaching, in order to get the CFT, we're gonna take a double scaling limit of these NS5 brains. So we're gonna get two NS5 brains approaches. So the string that we are talking about is propagating in the background generated by these two NS5, okay? And you can study what is the worksheet, at least the clustering worksheet that describes that background before introducing the open strings. And it's this non-critical string, okay, that Timo talked about, in the sense that it propagates in less than 10 dimensions, okay? It propagates in 8 dimensions. And here we can see that indeed all these other examples have the same string because you can construct them from the same clustering background. And all the differences just come from effects that are subleading in 1/n in the worksheet. Okay, so at large n, they are the same. Okay, so the same worksheet. And the third one that we didn't know about, it's just the same, but given by approaching 3 NS5 brains. Okay, so that's the background, and then you can also study the worksheet theory. Okay, so going to the conclusions. So all these CFT, all the CFTs in each of these universality classes, they share the same worksheet at large n. The difference is at sublead 1n. We know the differences, but we understand why. Each class is characterized by the number of NS5 brains that are colliding in this double scaling limit. So it's like you need to take the NS5 brains approaching at the same rate that the string coupling goes to 0. This confirms that there are, like the 3 types of weak coupling limits correspond to 3 types of string backgrounds. We can give the worksheet before the variation of the open strings. And then it's a different story, in my opinion, from flat space, because now it's like, you can say that they are fundamental strings, but it's like different towers, right? You have different worksheets, different exponential rates. So it's not like in flat space, we just say the fundamental string and it's 1/√(d−2). You have different values, and it actually opens a new Pandora box, like how many of these tensional strings can you have? This is just for simple gauge factors, but of course you can generalize for more than one gauge factor, which is going to include, is going to imply consider more than 3 NS5 brains and things like that. So we also discuss this a bit in the paper, so stay tuned if you are interested. And what else? Can we get even more exotic things? What are all the possibilities and all the exponential rates we can have? So now it's the moment to explore all this is, and we'll see what happens in the future. So I think I'm running out of time. So maybe let me just flash the conclusion and thank you for your attention.
Thank you, Irene, for a very nice talk. We have questions.
Hi, very nice talk, Irene. I want to make a comment. Could you back to the summary slide of the first half of the talk?
Yes.
Thank you.
Let's see, it takes a bit, but
Yeah, sorry.
it's okay.
Here. Yeah. Okay. So something I wanted to clarify that. So something from our joint work on this is that it's not quite true that the emergent string conjecture implies the sharpened distance conjecture. It does in the simple one-dimensional case with no warping. But more generally, as we discussed in our paper together on this, it's complicated to show that in theories with more than one modulus, and it's especially complicated in these situations with warping. So I think it's maybe not quite right to say that what you've done here provides evidence for the emergent string conjecture, because the situation that you were doing was inherently considering a compactification limit. So we know that the emergent string conjecture is true. But I think what you've done here is you've given very compelling evidence that the emergent string conjecture, in conjunction with the strong de Sitter conjecture, leads to the sharpened de Sitter conjecture bound.
Yeah, no, I agree. I mean, I put here, I say associated bounds. I mean, it's because you have, they are related, right? It's the exponential rate of the tower, but I agree, we have more directions. It's not obvious to show that that's going to be the lower bound. I also put the emergent string conjecture because that's also what the story is different in ADS. It was also related to that, so I mix both. But I agree.
So there's a question from Gary.
Yeah, hi, Irina. Here.
Well, yes.
Oh, nice talk, very nice talk. So some time ago, with Douglas, Toroba, and Underwood, we studied Kähler potentials for warp compactifications, and this was later revisited by Severin and collaborators. And the story is tricky because when you promote the modular hydrogen field, the equation of motions are not solved and in the presence of warping. So you could introduce a more complicated metric ansatz that we call compensators, or alternatively using the Hamiltonian approach that you have to solve the system with constraints. So you are going through that KK tower very quickly. I was wondering if you take that into account when you analyze the exponent.
Yeah, I mean, notice that the explicit results I gave are only for codimension 1. So you are just compactifying one dimension. Many things simplify there. Okay, it's much easier that when you study the complete general case. So, I mean, you can go, we can discuss later if you want, like all the sublattice and details, but I think for codimension 1, it's easy to get this universal result.
Okay, one very short question.
Yeah, I was wondering when you compute the distance, do you just compute the geodesic distance because you had a potential? And I think you have also worked on other proposals of distances when you have potential. So that's what I was wondering.
For the warping, right? So
yeah.
The thing is that in that case, the lower dimensional theory is Minkowski. So even if you have a potential in higher dimensions, there is no potential in lower dimensions. So that's why the distance is just the geodesic distance in the modular space. So that's what we compute. Now, if you generalize this story beyond Minkowski warp compactification, so including like some, other, the external space is more complicated, then you can also study what is the relation now between this Kaluza-Klein tower and that potential, and then which distance to use. But that's, we didn't get into that.
Okay, one last short question here.
Nice talk, Irene. So the upper bound for the alpha, you said that gets also decreased by the warping effects. Could that, first of all, is that known how much it can be reduced, and could it be reduced all the way down to 1?
Well, if you take the, let me just quickly. Yeah. Right, so you're saying, okay, this is the upper bound that we give. Now with the warping, this is the right result, right? So it's gonna depend on each case, what is the gamma that you have for the potential in higher dimensions. And it can decrease as much as you allow gamma to decrease, let's say. So it can get up to the 1 over square root of d minus 2, if you allow, if you saturate the bound for gamma. But still, I mean, the upper bound will still be given by the result without warping. No, like if we are just giving a bound in general, no, of all the possibilities that we could have in the string landscape, then I think the correct thing is that the upper bound.
That includes the de Sitter conjecture bound. If you put it in, what do you get for the upper bound?
Well, let me say, so the upper bound is when gamma goes to infinity.
Oh, the other way. Okay.
Exactly. So it's as large as possible.
I mean, what's the smallest it can? I'm trying to say that you have found examples where that's not true. There's a lower value.
Yes.
So the lowest value of the dimension 1 is what I'm asking. The lowest value.
Yeah, but the lower value is going to depend on how small is gamma. And then you can ask, okay, in practice, okay, this is in general, you can ask, okay, explicit examples, no? What is the smallest you have found? Yeah. Well, I guess you could even saturate it because, for instance, if I take, let me see, I think, no, so Polchinski-Witten is larger, it's in between, okay, it's 5 over square root of 7. But if I take, for instance, some 4D flash compactification with some membranes, BPS membranes, I think there's an example that could saturate this. And then if I compactify to 3 dimensions, then I would get as small as this. In higher dimensions, I think it's always in between the examples I can think of, but I will need to check which is the smallest one.
So I'm sure these discussions can continue over the coffee break. And let's thank Irene for a very nice talk.
Okay.
And we are setting up for the last talk of this morning session before coffee, which will be not less than 6 lessons on gravity decoupling. And the speaker is Fernando Marchesano. Please go ahead.
Okay, thanks a lot, Magdalena. And let me also thank the rest of the organizers, Mikel, Vince, and everybody for putting up this very nice conference here. I think we are all very happy, right? So, hi to everyone. As Magdalena announced, the plan of the talk is to talk about 6 things that I learned myself when I study gravity decoupling limits. And more precisely, is based on these 2 previous works and a work in progress that involved all these people in here, all of them in here, actually present, like Cristian Ufia in Madrid, Gonzalo Casas in Madrid as well, Alberto Castellano, you heard his talk in Chicago, Luca Melotti in Munich, and Lorenzo Palloni also in Madrid. Okay, so the motivation for this talk is something that you have seen over and over and over in this conference already, which is a distance conjecture, which I think is very fair to say that has given a lot of activity and a lot of insight, and poking into this conjecture has given us a lot of things to think about. The picture that a bit summarizes the distance conjecture is this one. You go along an infinite distance limit, okay, you take on this field, and you have this tower of states that go to 0 mass in Planck units exponentially fast. When you hit that scale, you have to leave the field theory description that you have. You just have to change it because you have to integrate in all these infinite towers of states. And at some point, you completely break down in any EFT description because you hit this pieces scale. Okay, let's summarize in 20 seconds. Now, what I want to point out is that there are 2 interpretations that you could give to this picture. One of them is something that David mentioned the other day, is if you insist on having a cutoff of your effective field theory, what's going on here in the IR, that is fixed in Planck units, because this tower is going down very fast in Planck units, at some point you hit it, and you just need to chop off your field range. That's it. After that, you need to change your picture and think about something else. And when the species scale comes down, then it's already more dramatic. That's one interpretation. A second interpretation is imagine that I managed to have some dynamical degrees of freedom all along the way. I have some effective field theory description, some degrees of freedom, maybe not all of them, but some that remain dynamical, that I can here in the IR, play with them, have a theory, have some dynamic something. All along the way, the limit. Even if this picture tells you, oh, I don't think you can, but you do. Then what it's telling you is the cutoff of your theory, which is at most this M star, this tower scale, goes to 0 in Planck units, or the Planck scale goes to infinity in units of the EFT cutoff, which is the statement that people throw when they want to talk about gravity decoupling. So in the second interpretation, what infinite distance limits are limits of gravity decoupling, okay? And that's why the motivation, because what I'm gonna do here, just like many other speakers before, Max, Mariana, and so on, here I'm going to study limits of infinite distance, but with this second interpretation in mind. Now, when you think in field theory terms, there's two well-known mechanisms for decoupling fields, one sector from the other. There's one no fact, but let me just put them in here so that you know precisely what I'm talking about, but there's some confusion. Very well-known mechanism is the mass decoupling. You have two sectors. One of them is very heavy. You put the typical mass of the sector A as a cutoff of the sector B, and then you integrate out all these fields, and the VEPs become the parameter of your sector B. That's the mass decoupling that we all know and love and use many times in compactification with potentials. The second one is the interaction decoupling. You don't have a hierarchy of masses, but you suppress the interactions between these two sectors, such that in some way, in sector A is not super heavy, but you manage to solve the equation of motions for this sector without caring about sector B. And then once you solve them, these are parameters in the sector B. Okay? The second one is what's going on in gravity decoupling, because we are not giving a super large mass to the graviton. And it works very similarly when you think about for the n equals 2 compactifications and for the n equals 1. So what I'm going to do is to look at this, an infinite distance limit in for the n equals 1, n equals 2, see what I learned, and eventually you can apply it for the n equals 1. So how does it work for string theories? You are string theorists, you know how it works. This is a subject that is extremely close to the heart of this conference series. So mostly, I mean, it's not the only mechanism, but it's a super popular, very powerful, and it gives us a lot of geometrical insight, is use localization properties that we obtain when we study string theory. You can do geometric engineering, you can use the localization properties of the branes, F theory, all these things that have been powering this conference series for a very long time. And also used in phenomenological applications like crazy. There's more, there's warping. But these three, I think they are like really close, at least one of them to your heart, okay? If you're here. Okay, so the general pitch that you get when you do this is that, okay, gravity is diluted as compared to all these localized modes that you get because of your compactification in some internal patch. Gravity is all over the place. These guys are in localized, oh, where are you? Localizing here, gravity is diluted, weak, and these guys are strong. Okay, very nice. This is not untrue, but some of the lessons that I learned told you that is a little bit more complicated than that. So in here, because as I'm going to do for the n equals 2, I'm going to focus in particular to gravity, geometric engineering. The geometric engineering that we have seen already in several talks in here. And more particular in type 2 string theory compactifying a Calavilla, which is a very well-known setup, the one that started the whole business of geometric engineering and that people have studied a lot. So the point is that along these infinite distance limits, you can like engineer this geometric engineering if you go along them in certain cases. Now, an important point is that most of the talks that you hear about infinite distance limits They don't result in some geometric engineering. Like the things that we have seen when we studying in these papers is that you can get cyber-Witten theories, 5D SCFTs, dimensional reduced to 4 dimensions, same for CZ SCFT or little string theories. But that's not what you hear in the average infinite distance talk, because usually what they focus is in vectors that have nothing to do with some degrees of freedom surviving here. That what I'm gonna do is to consider those infinite distance limits with something survives below the distance conjecture scale at any point of the limit. Okay, I want to do that because, okay, these are gravity decoupling limits, but I want to decouple them from something. This something is here. And it's when you take that into account, when you understand how these gravity decoupling details work. If you have nothing to decouple them, okay, that's kind of a empty statement. And with respect to geometric engineering, what you do is you place yourself at the end point of this picture. You already decouple, forget about gravity. I don't want to do that. I want to take the journey of the gravity decoupling to the endpoint. I want to enjoy the journey. Okay, I hope you enjoy it with me. And I want to learn something about the journey. And this talk is about what you learn or what I learned when I did that. And hopefully you learn something too. Is that okay? All right. So I try to make it not technical, so because we don't have a lot of time, but let me just pitch the two strategies that we use combined to get something out of this story. There are two very, very well-developed, well-known techniques to analyze the spectrum of states, particles, objects, the couplings that you get in this kind of limits, how they evolve, and so on. One of them is a special Keller geometry, like already developed in the string theory context in the 90s, which relies in some prepotential that gives you all the couplings, masses of VPS particles, all kind of things, everything from the prepotential. This also encoded in this period vector. And what is more, it has a very precise notion of what is gravitational and what is not gravitational coupling. So, for instance, the curve potential that you derive from the prepotential, if it has a log in here, you are in a gravity situation. If you didn't have the log in here, you are not, which means essentially in the metric, if the term dominates, you are in a rigid field theory situation. But if everything in here is important, equally important, you are in a gravity, you're seeing a gravitational moduli space metric. And second is this recent development of asymptotic gauge theory, which many of our colleagues here developed like a few years back, in which you have an expansion of the periods that is a bit different from this one. I mean, it's an expansion based on that some fields that are periodic, and that has a leading term that displays some axionic shift symmetries, and then some exponential terms that break them. So it's an expansion based of an axionic shift symmetry. And this is going to play a very important role because related to axionic shift symmetries, we have axionic strings. And also the advantage of this approach is that this is going to also be true in for the n equals 1, even if when we don't have some prepotential description or something similar. Okay? Okay, so let me tell you about the 6 lessons. I'm going to go one by one and quickly because I think I don't have a lot of time yet. So lesson number 1 is that gravity is not alone. Okay, you can say, oh, I have a gravitational theory, there's a graviton, there's a graviphoton even in n equals 2, and I want it away because I want to decouple gravity. That is true, but it's not the only truth. And okay, let me tell you exactly what I mean. One way to analyze this problem is to look at the PPS objects, operators, or whatever you want to call them, the particles and strings that you have coming from your compactification. And you can analyze them and you can classify them in terms of the charge to tension ratio, the charge to mass ratio that Irene was just talking about, that Mariana also talked about. They are BPS and extremal if this is order 1, okay? Which was a key object in all this classification of infinite distance limits. This means that the gravity and the electromagnetic charge are equally important for these objects. So gravity is meaningful when you compute the forces that interact among them. But it can also be BPS and non-extremal, which means that this ratio goes to infinity. Gravity is almost irrelevant. And basically, if you want to understand the dynamics of these objects or how they interact, you just can forget about it. And then you can apply the specification to the two, I mean, you have several objects, but here in this talk, two of them are going to play a key role, the BPS particles and BPS strings. As I told you, there is a lot of axionic shift symmetries going on in this limit, so you're going to have axionic strings. You can ask what it means that this gamma is order 1 or close to infinity, or very large. And what it means is that this term is more important than this one or is not, precisely the definition of rigid metric or non-rigid metric. When gamma goes to infinity, this is much more relevant than this one. For the strings, the particles, sorry, you have a similar statement. You can split the physical charge into something that's proportional to the mass in Planck units and the charge that you would compute if you were in a rigid theory. So when this gamma goes to infinity along this particular limit, infinity distance limit, this is going to be much more important than the mass. Okay, that's almost tautological. Very good. So the gravitational sector of your limit is essentially these guys, the guys that are extremal, and the fields that these guys are charged on, okay? And along any limit, I can tell you already a few guys that are there, and there are always more than one. Are you kidding me? Okay, let me rush. So the leading direction of the limit is associated to axionic BPS extremal string that are the EFT strings that you have heard in previous talks. And it's always there. It can be more than one, but it's always one. And the distance conjecture tower is extremal BPS particles, as was shown in this works in here. So it's another extremal object. And these two extremal objects are associated to vector multiplets that are independent. So you not have a graviphoton that you want, there's a graviphoton, and the graviphoton talks to several vector multiplets always, okay? Which means that if you want to decouple gravity, you not only need to decouple from the graviphoton, you need to decouple from all these vector multiplets that are associated to it. So let me give you, because I'm running out of time already, let me give you what is the picture that you get at the end, and I'm going to develop on that. The kind of structure that you get when you think in terms of vector multiplet or field directions or whatever, is that you get a bunch of guys that are extremal. There is a bunch of guys that are rigid. You see a rigid mutual couplings, but they do not really decouple from the extremal ones. And then you see another ones that really do decouple from that. This is what we call gravitational, core RFT, rigid field theory, and extended RFT. And if you want to have a picture in terms of geometry, which I guess you do, this will be, in case of type 2 large volume, there will be NEF devices that are like the M-theory supergravity string things that go decouple when you decouple gravity. Then you have these non-effective devices, but nevertheless grow. And these are shrinkable devices with which you do the geometric engineering, okay? Lesson number 2. There is a favorite scalar potential, okay? We all have been learning since we were very small children that there's a thing called scalar transformation in supergravity, and that is very important. It is also true that there is these results, Komarkovsky and Seiberg, and then Adams et al., that if you want to have weakly coupled gravity, you need an exact scalar form in your moduli space. It needs to be exact, which means that, okay, I don't know what's going on here, but for sure in here, this guy is exact. I don't need different patches to understand and to describe my metric. I can do it with one. Now, how do we see this in asymptotic limits? Very good. If you take this Simpleton-Orwin theorem and you look at this expression of the periods, you may try to do Keller transformation on this guy when you interpret it as the periods of a holomorphic 3 form in type 2b, for instance. You can see that the Keller transformation that would leave this expansion invariant are the ones that the famous F is constant, which means the gradient of the Keller form is fixed. I mean, I can do a Keller transformation that I want, but then I will lose this structure, which I don't want to. So this guy is fixed by this. And the physical interpretation is that when you have this structure, you have a leading term in the Keller potential that has some axionic shift symmetries. the tension of the BPS axionic strings is computed as the derivative of the Kerr potential, which again means that this is fixed. So you have a frame in which the computation of the tensions of physical objects is very direct. It are the components of the gradient of the Kerr potential. And if you can do this for all directions, you essentially are fixing the Keller frame. Again, what this also means is that the leading distance conjecture tower, the lightest extremal BPS particle, is of this form, essentially a constant times the exponential of the Keller potential, which again fixes the Keller potential. And this is something that's going on all over the region that describes your asymptotic limit. So you're again fixing this because you're taking a gravity decoupling limit, and by this result you will have to have an exact Keller form. What this is giving you is a physical source of where this fixing comes from. Okay. Incidentally, this mass is also the one that you should take as a reference scale for your effective field theory. If you start writing your prepotential for a subsector, for this rigid subsector in terms of this scale, you recover the usual formulas of rigid special Kerr geometry. Lesson 3. So the kinetic mixing is directly related to charge vectors. Okay, let me see that as we go. So for particles, you have the no-force condition, like interacts between the charge, the mass, and the exchange of moduli. We learned this from Iran some years ago when reinterpreting the identities in Ceresole et al. And then, as Mariana was telling us, Ariane as well, there is a very nice way of analyzing this kind of physics in terms of the charge vector, which is the gradient of the log of the mass of the object. Okay, something that has been exploited in several papers that wanted to analyze and classify infinite distance limits. Now, in terms of the charge vector, this vector field in moduli space, you can express the no-force condition between mutual BPS particles in here, like this, and because it's proportional to the charge to mass ratio, the norm of this vector will be order 1 for extremal BPS particles when this mass is of an extremal BPS particle, and it will be super large when it's non-extremal BPS particle. Now, what is also very interesting, and it was exploited in previous talks, is that the products of these guys are the one for the extremal particles. And that you can also consider this if you have axionic BPS strings, as was also developed here in the case of EFT string case in several setups. Now, I'm going to use this to get a point. For instance, if you take into account the two things that I told you, that that the gradient of the Kerr potential essentially gives you the charge vector of the leading tower, and that the BPS axionic strings are computing like the components of the gradient, you get this relation, the product equal to 1, which is nothing that the pattern observed by Alberto, Ignacio, and Irene 3 years back. What I'm going to do with this pattern, well, I'm going to show you something very simple. If I have this product fixed, and I have one of the two vectors is the gradient of the Kerr potential, the second one is something that can be of a short norm or of a large norm. What is going to happen is when the norm is very large, this is going to be orthogonal. Okay, trigonometry. This is easy geometry compared to what you do every day at breakfast. So here, what is going to happen that all these rigid sectors are orthogonal to the gradient of the Kerr potential, which is something that we have seen again and again and again and again when taking rigid limits in special Kerr geometry or all the setups. I mean, you just take a Kerr potential and you expand because this piece is much larger than this one. Okay, this is the usual expansion that gives you a rigid metric when you do, and this goes back at paper Xavier Witten and even. Okay, but this geometrizes this story and translate it, which is very important, into objects and directions that are related to quantized objects, like strings with quantized charge and particles with quantized charges, which are quantized directions in field space. And key objects, they have a meaning in this, meanings like the distance conjecture. Now, the actual structure that you get is this one, And you can interpret it because when you take products, normalized products of the things, what you get is the kinetic mixing between field directions, okay? Quantized field directions, this is very important. And the gauge kinetic mixing when you talk about products of particle charge vectors. And the structure that you get is the following. This is the extremal sector. They are some angles, but not very large. Then you have an orthogonal set of rigid sector that is splits into two, the one that doesn't really decouple from gravity, in the sense that I will talk about later, if I have time, and then the one that really decouples from gravity. And this one, actually, what happens is that you have charge vectors of electromagnetic pairs. You need both the magnetically charged and electrically charged. So, in other words, the orthogonal sectors in tangent moduli space decouple from each other at the kinetic level, which is one of the things that you need to do to get gravity decoupling. Now, this statement in here is completely trivial if I don't input that these vectors are quantized because they come from particles and states and strings with quantized charges. And that's what gives them a meaning, because they have a meaning in terms of U1 charges. Oh, right. Lesson number 4. I'm going to do it in 20 seconds, apparently. So the role of moduli space curvature. So for gravity decoupling, we need like two things. One, no significant kinetic mixing. That was covered for orthogonality, but then no mixing at the level of interactions. Okay, all the interactions that may give you a mixing are important. For instance, mass mixing could be, this is not the case here. We have a moduli space, but we have polycouplings. The polycouplings, the interaction between different vector multiplets, they actually can be rewritten in this way when you normalize them, when you look at physical Pauli interactions, with these kinetic terms, and they measure how these things interact with each other, with the exception of n equals to 4 sectors, okay, which you can have enhanced supersymmetry. And then what you can do is to write the curvature in terms of the Pauli couplings, and what you should demand in order to decouple the field theory sector that you want to demand is that the Pauli interactions are much stronger in this sector than it's mixed interaction with any other sector. For instance, the geometric intuition, if you compute the curvature, the curvature from the field theory formula, you're going to have, sorry, from the supergravity formula, you're going to have something like this, where here they can be the rigid indices or the mixed indices. So you have going to have the field theory prediction plus something else. This something else needs to be very small. Otherwise, the curvature that your field theory predicts is not the one that you see in supergravity, and you have not really decoupled the other fields. Whenever you do this, for some reason that we don't really understand, you lead to a curvature divergence. This hierarchy, because this is typically order 1, this needs to be very large. And that's why you get a curvature divergence that typically takes this form, where this is the quotient of the distance conjecture. Okay? And is typically bounded by the Chern-Mass ratio of this RFT. Okay, lesson number 5. Oh, yeah, okay, sorry, yeah, okay. Lesson number 5, the decoupling can be described at the level of monodromies. And that's gonna be very short, I assure you. Actually, what we observe is that to describe this sector of the effective field theory that fully decouples also at the level of interactions and so on, you can do the following statement. If you have the monodromy that you get along the limit, associated to the axionic symmetries that you have along the limit, whenever this monodromy, the associated monodromy group splits into a block diagonal form, then is when you can have the decoupling. If you don't have the split, you don't have the decoupling, okay? What this also means is that all the interactions in here with the vector multiplets whose fields have a Planckian web, they're exponentially suppressed. So even if you have a Planckian web that takes you very far away, you have an exponential suppression that will kill it. And that's how you decouple from the sector, which is the tricky part of the decoupling. Lesson number 6, sorry, Magdalena, in finishing. The decoupling theory always seems to like effective cycles, okay? In all examples that we look at, there's an effective cycle in the local geometry. And this means in one way or the other that you have a tower of states associated to your geometric engineering theory. For instance, you can have the Cyber-Witten-Dion tower, the 5D SCFT tower, et cetera, et cetera, et cetera. In the Cyber-Witten case, what you can also see is that the decoupling is not always for granted. And you can translate this gravity, this decoupling at the level of interaction or the curvature divergence as the fact that you decouple the Cyber-Witten scale, the Dion tower, from the species scale. And the interpretation is that you have a rigid UV completion given by the Cyber-Witten tower that is way below the gravity UV completion, which is a species scale. When you manage to do that asymptotically, parametrically, is when you have the decoupling, when you have the curvature divergence, and so on and so forth. Now, is this a general lesson? No, okay, because there's a counterexample, but the counterexample is very specific, yes and no, which is whenever you have a limit in which your rigid field theory is a little string theory. There, this picture that I show you doesn't really apply. They're at the same mass, and the decoupling should follow some other rules. Okay, so I'm out of time. I was abundantly pointed out. So I'll leave you with the conclusions, and thank you so much.
Thank you, Fernando, for a lovely talk. We have time for one or possibly two very short questions.
Thanks for the nice talk. So in many situations where you engineer a field theory, it comes with a flavor symmetry, and it would be characterized as being a non-isolated singularity. So there's a core singularity, then there's another singularity. Where does that fit into the? Is that part of your lesson one, or?
I mean, the flavors are part of this. Oftentimes, they are part of this rigid sector that doesn't decouple and appears parameters of your decoupling theory. I don't know. Like, I mean, I don't know if that's part of lesson one. You mean because I mean, part of the lesson one or all the other lessons, I don't know, one is that all this information that you decouple stays in some way, which is something that people know, which are the mass parameters and all the kind of parameters that you get in rigid field theories. But I don't know if this case will be the case. You can maybe explain to me better and see if it is.
Any more questions? So if not, let's, oh, sorry, there is one there. Yes, go ahead.
So can you turn tables round? Does this tell you, can you see with the naked eye when a field theory cannot couple back in any way?
Oh.
By these elaborate rules?
I don't know. Because you mean if you are in the geometric engineer setup where you have already decoupled gravity? No, I think that's a bigger question. That's a very interesting question. But I don't know. What you're asking is a bit meta, because you see, I'm doing gravity decoupling limits, and the philosophy of the Swampland is that all the Swampland lessons and conjectures should be trivial in gravity decoupling limits. So I'm like I'm doing this extremely complicated gymnastics to put it back into the Swampland philosophy. But I think it's a very interesting question. I don't think I don't have, no, I mean, not so far. Thank you.
Okay, so let's thank Fernando again first. I have two announcements. One is that the speakers of today must make sure that their slides are shared with us organizers so we can put them in computer. Second announcement is that now we have coffee and we will reconvene at 11. Okay, so please find your seats. Before we start, is this on? Can you hear me in the back? So before we start, let me tell you that if you are interested to see the main auditorium of this building, which is downstairs and which is a very grand auditorium, this will be open for us so we can peek into it at noon today, so after, just before lunch. And Magnus here will open the door. Okay, and now we proceed with a talk by Comrade Vafa, who will tell us about non-supersymmetric strings and geometry. Please.
Thank you. Thanks so much for having this conference. This is an amazing conference. I'm very much enjoying it, hearing all these amazing talks and people to interact with. Thank you. Thanks to the organizers. It's beautiful, beautiful place as well. I'm going to talk about non-supersymmetric strings and the relation to geometry, a topic we don't hear much usually in string theories because we don't know much about them, unfortunately, even though our world is non-supersymmetric and we have to get to know and feel more comfortable with it. So that's my hope, to try to get a little bit more comfortable with these things. We usually talk about weak coupling regions of string theory and strong coupling when we talk about supersymmetric theories. But when we talk about non-supersymmetric ones, we are more or less stuck with the weak coupling corners, and we don't have much to say about the rest of it. We see tachyons, we see things. We have these conjectures about how the potentials work on non-supersymmetric theories and so forth. So it's about time to go a little bit more in depth into the core of the moduli space, or into the core of regions where we don't have good weak coupling descriptions, and in particular use robust ideas perhaps from topology or from symmetries and combine them somehow. And that's my goal here. It's related to the number of works I've done with a number of people: Chen, Van Dijstik, Bicara, Delgado, Dudas, and Parra, deFreitas. The next talk after me is by Hector, who's going to continue some of the discussions related to some of the topics I'm going to talk about. And it's based on these papers here. So the geometry of the light moduli states is going to be my main focus. So we have light moduli. In non-supersymmetric theories. Now, light moduli is slightly different from just moduli, because in the usual case, we have, when we talk about moduli, we really mean strictly massless. But in non-supersymmetric theories, we have to embrace the fact that there will be potentials. And so you would be writing a potential, so there may not be quite massless fields, but the light fields. Things like dilaton and things like tachyons that we are familiar in the context of string theory. So trying to find the exact potential is a little hopeless in these kind of situations. But what one can hope to do, perhaps, is to find the topology of the space. How does it look like? Topology of the space, including points which are symmetric points. Namely, you have points where you think about it as a bigger space of the full space of phi I divided by some group, which is the duality group. And in particular, understanding the structure of fixed points would be very helpful in this context. And the reason that would be helpful is that I have a better marker. And the point would be that if I find those points, if there is a group acting on these which fixes an isolated point, what that means is that at that point, if you have a point phi I star, for which is fixed by G, and any direction you go will not be an invariant point, that means it's an isolated point. At such point, the gradient of the potential will vanish. And why would it vanish is because if you expand it, you will have V equals to V naught plus, alpha I phi I star, dot, dot, dot. This term, since these phi I star are charged under the discrete gate symmetry, which is the leftover fix, which is the symmetry that's fixing that point, which is a discrete gate symmetry of your theory, implies that the linear term vanishes, and so you automatically get critical points. So this will be a very effective way to find critical points, even if we cannot compute V. Now, this strategy has been used in some contexts, in particular in this paper here from last year, where we basically considered the flux vacua of type 2B for some non-geometric compactifications involving Landau-Ginzburg theory. And in those cases, in type 2B orientifolds, we found that you have the type 2B moduli and some complex structure moduli. And at some points where you have very, very special complex moduli of the Landau-Ginzburg theories and very particular values for the couplings, like the third root of unity or I, which are the interesting points of the symmetry of the SL2Z, we found that we could basically reproduce the results of Mariana and company, as well as Tim Rossi and company, where they had already found some examples of critical points for non-supersymmetric theories, and extended to get some additional ones, including ones with V positive as well as V negative. So we could find potentially unstable de Sitter, as well as anti-de Sitter and Minkowski ones, based only by symmetry principles of the theory, which is quite makes it robust as far as the existence goes. So we were trying to see if we can extend these ideas to more general classes of theories, non-supersymmetric theories, but it came to our attention that we haven't even understood the 10-dimensional ones, let alone the compactifications of the other ones. So instead of going down and starting with a supersymmetric theory and compactify it and get non-supersymmetric vacua, it would have been interesting to already go back to 10 dimensions and understand them directly in 10 dimensions. So, so that's the goal here now, is how do we address the question of understanding the geometry of non-supersymmetric strings already in 10 dimensions? Now, but I will take one step before I get to there, which is we can even simplify the discussion here by a very trivial compactification, toroidal compactification. Now, toroidal compactification, we are familiar as a supersymmetric example, but we can also make it easily non-supersymmetric. How do we make it non-supersymmetric? Well, it's probably one of the oldest ways to break supersymmetry of a supersymmetric theory is Scherk-Schwarz mechanism. So we want to study Scherk-Schwarz mechanism. Basically, you put the theory, like M theory, on torus. Now, if you put periodic boundary conditions, then it would be supersymmetric. But what you can do is to make one of the circles anti-periodic, or basically make the spin structure not trivial. You break the supersymmetry easily. And this is a very simple way of breaking supersymmetry. And in that context, it's natural to ask, as a function of the moduli of your theory, are there points for which grad V equals 0? Are there any critical points? Now, of course, in the regions we can compute when this is large and so forth, you can show there is no such critical point. So therefore, you really have to understand that the Planckian distance length scales, whether there could be critical points. That's going to be very hard. However, it's not that hard to actually identify some of these based on symmetry. So I would try to give you an example, which we just did recently in the past week. A simple example is take M theory on T3. So take three circles. So first of all, let's do the periodic ones. This is the usual supersymmetric one. 3 circles with periodic boundary condition. And this is the M theory picture. Of course, there's a 2A picture where you just keep this piece. And this is the 11th circle, in other words. And then there's, of course, a 2B picture where you dualize, the T dualize this circle to another circle. And so you keep this circle, but you dualize this circle, T dualize that circle. This theory has a duality symmetry, which is SL3, coming from this guy, and then SL2 coming from this guy. So this is the U-duality symmetries of this theory, which is geometric. It's geometric of this and geometric of this. Combined together, you get the full duality group. So we understand this in a geometric statement. So now we put anti-periodic boundary condition, and I judiciously choose it to be this one. So I change this to anti-periodic boundary condition. And therefore, in this chain, nothing changes here. This is still anti-periodic boundary condition. And T-duality is acting on the periodic circle. Nothing happens. So this is still anti-periodic boundary condition. And now we ask which subgroup is preserved. Well, it's a geometric space we have put a spin structure. We already are familiar. This sounds like the worksheet of a string theory. And to genus 1, we are very familiar with which subgroup of SL2Z that's preserving. This breaks down to a order 2 subgroup of SL2Z just by the symmetries of the diffeomorphism group left over, which preserves the vector 0, 1, mod 2. So that gives you a subgroup of SL2Z, which is called gamma 2. And similarly for this one, the symmetries are just the same thing, which preserves 0, 0, 1 mod 2. So 3 by 3 matrices, which preserves this. And so we have a duality group, which we can derive, even though we broke supersymmetry, because it's geometric. So we can actually be sure that this is the correct duality group. So it's not lost. As we can see, the duality groups, even if we break supersymmetry, can sometimes be deduced very reliably here by diffeomorphism invariance. And we can then find critical points. How do we do that? Well, we have the symmetry points. We can go to isolated points, and it turns out there's an analog of tau equals to I, which is a symmetric point here. And similarly for this one, there's also an isolated point. So therefore, you can choose a totally an isolated point of the duality group, which gives you a critical point for the potential. So in particular, if you, the simplest way to describe which point it is to choose all 3 to be anti-periodic. So you find you put 3 anti-periodic, well, maybe I should say it differently. If you had 3 anti-periodic directions, that would have been easy to understand in terms of the symmetries of the torus. But the easiest way is, instead of this, start with the 3 periodic directions, S1, 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 and make their lengths to correspond to, in the type 2A picture, in the second line, to correspond to self-dual radii. Turn on is C1, 2, 3 is equal to 1. And then mod this out by its translation by a diagonal. So you come out diagonally out by half of the vector. So you say half of the diagonal, you shift it, and at the same time, put a -1 to the f. So if you mod out by this with a -1 to the f half shift, this is the fixed point. This point is the critical point of the shared shorts. So it's a Planckian length, and all 3 lengths are equal, and you can know which length it is from the type 2A picture. We also generalize these to other dimensions, and in particular, we found similar solutions in the case of so d equals to 4 and 6 in particular. We had other example in 5. But for example, for d equals to 4 and 6, exactly this construction works. That is, you can take the same torus of the right dimension in M theory, take them all periodic with the radius to be self-dual 1, and turn on Cijk is equal to 1 before shifting by a half. Cijk equals to 1 naively is trivial, but if you shift by half, then it becomes non-trivial. And all theCijks are turned on to be 1 for all the triples you choose. Again, that you can show as the critical point. In the midst of this, we learned a fact that it was amusing in its own right, so I will mention it briefly. So identifying as doing a circle modification involves modding out the circle periodic by a shift. You mod out by a shift symmetry accompanied by a -1 to the f. The shift symmetry could be itself viewed as some action like e to the I vector times the momenta of the corresponding lattices that you're doing, accompanied with a -1 to the f with some shift vector v. So geometrically, we can do this, of course, and that's what one way of describing what we are doing by putting this anti-periodic boundary condition by starting with the periodic one and quotienting by Z2. You could have done this in general, involving in the context of the Narayan lattice, you will have the p left and p right. You could have shifted by e to the 2 pi I some shift vector, which could be some order n, maybe if you want to do the more general orbifolding with something, we are doing order 2, so that would be an order 2 version with an extra -1 to the f. This, of course, we cannot do arbitrary shifts here, because if it's left-right symmetric, it's okay. That would be just a usual geometric shift. But in general, you have things involving level matching, which generally gives you a formula like 1/2 A left squared minus A right squared is 0 mod n. This comes from the modular invariance of the worksheet or the level matching condition of the worksheet. And it turns out that when we were studying this more general one in M theory, this got a generalization, which is quite amusing, which turns out to be related to modding out the charges. If you have more general modding out an M theory on a toroid with some charges, it turns out that this shift vector satisfies not just this quadratic equation, but the more general U-duality invariant quadratic relation, which was somewhat unexpected for us. For example, if you then down on M theory on T5, then the U-duality group is SO55 with integer coefficients, and the charge lattice corresponds to spinors, and this A corresponds to a dual spinor when you want to choose it. So if you have a mod n condition version of this, it turns out to be the condition for the viewing this A itself as a spinor. It turns out that the condition is that A is a pure spinor mod n. So the condition of level matching becomes something which is quite unexpected in the language of a U-duality invariant statement, and this would be better to understand. It would be good to understand this more deeply, but this is what we found by doing U-duality transformations on the level matching conditions. So it must be true, but it'd be interesting to understand it better too. So let me then move on to the 10-dimensional one. Suddenly we want to graduate and go all the way back up. So we see that the circles are almost good enough. So let's push it down, push it up all the way to 10 dimensions. So in 10 dimensions, what are they? I'm going to focus on 3 theories in the remaining whatever time I have: 0A, 0B, and SO16 cos SO16 heterotic string. So what is 0A, 0B? This is just 2AB mod out by -1 to the F. You just basically get rid of fermions. What happens? No fermions, no light fermions. It doubles the number of Ramon-Ramon fields, and you get an extra tachyon. So you get a tachyon field and these. So for 0A, the light moduli field would be the dilaton and the tachyon. For 0B, the light moduli I'm interested to understand is the original axiodilaton coupling. Axiodilaton coupling, and now you get a tachyon, but the tachyon also gets an extra component because I said it doubles the RR field, so you have an axiodilaton component chi prime coming from that, so you get actually a complex complex component, extensional tachyon. So you have tau, and judiciously I call it Z. So the question is to understand the geometry of these parameters. That's the goal. And what can we say about this? So since I have very little time, let me say that one idea would have been that 0A should be related to M theory on a circle with anti-periodic boundary condition. That would have been the most natural expectation, and it has been proposed, but unfortunately this doesn't work, and I don't have time to explain it, it's in our paper, so this doesn't quite work. So we have to find a better way of doing a 0A description from M theory. And the way to do it is to actually be a little bit more courageous and maybe a bit speculative. And that's what I think is what drove our project, not to be worried about exotic objects that might be natural in this context. And that's what we were trying to do to understand it. So what were we motivated by? We wanted an M theory description. We said we are looking for M theory description, and M theory because it has a 2A version. So if there's a -1 to the F here, you would think that there is something you should be able to do on M theory. If this doesn't work, then something else should work. What can it work? And the proposal was based on the idea that the 0A theory, to understand it is here we remember that there's the Ramon-Ramon 1 form, which therefore gets related to the U1 coming from the KK reduction of M theory. So the existence of a gauge field led to the natural description of a KK tower, the zero branes. For 0A, we have two gauge fields. And so it's natural to expect two circles, one for each. The problem is that this will be 12-dimensional if you multiply them. And if you don't multiply them, it will be disconnected. So we wanted to have a theory on a circle or something like a one-dimensional space with a U1 times U1 isometry. Doesn't exist. Okay, so geometrically we are doomed. It doesn't work. However, we said, let's imagine that there is a notion of function space on a one-dimensional space which behaves as if there are two U1s. How would it look like? Well, it should be more or less like this, but they should somehow talk with each other. Well, we said the most natural way to talk with each other is if you kind of identify 2 points, like a figure 8. So basically what's called S1 VS1. But if you do that, of course, you have to be very careful. First of all, the fields will not be quite well defined at this point. You have to tell me what do I mean by continuity condition or smoothness condition at that point. And then you can assume, well, fields somehow become resolved this way or perhaps this way, depending on which fields you're dealing with. So that's one possibility. So then you would have at pin the singularity because you have fields which could have both either way. And so therefore some fields live here and some fields live here at the same time. So therefore you cannot, it's like a frozen singularity. So that would be not unfamiliar to some of the things we have seen. So that's not as exotic, but the more exotic one is you want this point to be immaterial because you want to preserve the U1 rotation. So the choice of the point shouldn't matter. And that means you have to define the function space on this in such a way that you identify functions with movement of which points you have identified. So that would be, of course, a much more exotic space, not a regular manifold. It's like defining the space by the functions which are well defined on it. So this is in that sense exotic. It better be Planckian because if it becomes macroscopic, it wouldn't really make much sense. So the best hope we have is that this is a good description when things are Planckian in M theory. When they become big, there must be something preventing it. Something similar to the cork and their confinement. You know, they're fine when you get to the below the QCD scale, but above it, you don't see them because they're confined. So you should not be able to see them macroscopically. So in particular, the metric for this would look like, if I call those two circles, d theta plus and d theta minus, so you just write the usual fields and the usual gauge fields. So you do get the two Ramon gauge fields that you want, but in addition, you have fields like C mu nu rho plus or minus, and this will be living on disconnected resolution. And then, but you will also have fields like C mu nu and then plus or minus, but this should be living on the connected resolution because we only have one B mu nu. So this is the connected resolution of the space. And so you can actually organize all the fields of M theory in this form. And the fermions get massive, so I won't talk about those, but so therefore these are the light fields. And then you ask, what is the relation of these circle sizes to my fields? So you see you have two fields here, and it's natural, therefore, to identify them with somehow two circles. So what would the relation be? Well, the good hint is that if you look at the KK tower will be related to the two circles. And it turns out the mass of the D0, there are two D0 branes in this theory, D0 plus and D0 minus, as you would expect, because you have two circles. And if you look at their mass, they go like 1/G string, as you expect, but then there will be tachyon dependence. And it turns out to linear order, the tachyon dependence will go up or down, depending on whether you have a plus or minus D0 brane, which is therefore interpretable as saying if you start with equal size circles at tachyon equals 0, and if you change the relative sizes of the two circles, that should be corresponding to the tachyon expectation value. So the tachyon expectation value can be related to that in this form. In fact, if you're careful about coefficients, people have studied it up to order t squared, and up to order t squared, it agrees with the form which is this. So Garcia's conjecture that this might be the exact form, even though that has not been shown. Up to second order is true, but let me assume it is true. What would this mean? It would mean that if you approach this at some value of t equals to 1, one of these branes become infinitely massive, which would mean that at one point, when the circle shrinks to nothing, that you get rid of it completely, the kk tau. And in fact, you would think that that should become the same as M theory on a circle and should be 2a, so this should decay to 2a theory. And indeed, it has already been argued by Minwola and collaborators that 0a tachyon condensation should lead to 2a, and this would be compatible with this picture. So basically, you go from this to you shrink one circle and ultimately just to have one circle left. And you can map the tachyon profile with the G strings, and you find some relations for them. Tachyon goes like r plus squared minus r minus squared. And the G string goes like r plus squared plus r minus squared times r plus r minus. So basically this cubic relation, and this is the difference of the r's. So I see I have run out of time. So I will just say very briefly what happens in 0b and SO16 cross SO16. In the case of the 0b, the natural analog of this picture would be that here you had a circle and you had identified 2 points to make it look like this. That's another way of saying it, what we just did. You identify 2 points, you get a figure 8. In the case of the torus, you identify 2 points on the torus. So it's like if you want to think of it, you can think of it as a pinch genus 2 torus, where that pinching has to do with which points you're identifying. This choice, the distance between them, is the z parameter of related to the tachyon profile, shifted version of this. So in fact, the tachyon being 0 corresponds to one of the half points of the torus. So the modular symmetry in this case ends up being the geometry corresponds to the usual SL2Z, which acts on tau and z as z over z times theta plus d. So this leads also to the prediction of the existence of conformal theories, gauge theories, at RG fixed point, namely, which in this case descends down from ND3 branes. So if you take ND3 branes, you find that there is a critical point here at some particular value of tau equals to 1 plus I over 2. And what this corresponds to is that the prediction of the existence of a non-supersymmetric gauge theory having a conformal fixed point. So that conformal theory we are talking about is SUN times SUN with NN bar. So these are the fermions in here and some bosons which are in the adjoint. And you choose the gauge couplings to be equal for both of them and equal to with some turn on some theta angle. So it turns out that you can argue that this is a fixed point, the critical points of tau, which means that if you have an RG flow vector, the RG flow vector should be U-duality invariant, and at that point, there's no direction to go. So in the case of, in the last picture I draw, because I really am running out of time, I have run out of time, is the SO16 cross SO16 theory. This theory has a spectrum which has fermions in 128 and 1, and 16, 16. So these is spinors on one chirality, and this is the other chirality of spinors. As you can see, it has a chiral theory. The anomaly of gravity anomaly cancels because 256 is 256. However, this looks very much like two walls, but they cannot be separated because 16, 16 cannot become masked up because it's chiral theory. So what happens is that in this case, the description comes like this. You take this figure 8, but let me just, the figure 8, I'm just resolving a tiny bit so you can see it. The usual Hojava-Witten was you reflect on a circle, and this would have given an E8 times E8 as the usual one. But here they are stuck together. So if you do a reflection here, you get the same picture, but the two boundaries are the same. And this turns out to be our proposal for SO16 cross SO16, and also the other heterotic E theories. And some extensions of this has been proposed also by Uranga and collaborators. So since I've run out of time, I'll stop here. Thank you. And you'll hear more about it from Hector.
Thank you very much for a beautiful talk. We have time for one question.
Thank you for a very nice talk. A question about the backgrounds, in particular the metric that you've written for 0A. Is there a well-defined notion for the isometry of the background?
For this, the background, you mean S1 times S1 v S1?
Yes, S1 v S1.
It has to have a U1 times U1 isometry. By that, I mean, it's not a geometric isometry because we know that S1 v S1 does not have U1 times U1 symmetry. But you can define a function space motivated from S1 v S1, which does have it. In other words, you take a function which is invariant, which you say the function is invariant under the shifts, equivalence classes of them, so you can define it to have. So basically, the statement is that you define the function space, which has U1 times U1, because there is no manifold with U1 times U1 symmetry in one dimension.
Does this give rise to some possibility of doing something, a generalization of Kaluza-Klein?
That's what we are hoping. So there's, in other words, you're going to have to be more abstract about what is a good space, to have a compactification of how do you deal with it. I mean, we have seen similar things in non-commutative geometry where you can define motivated by a manifold, but actually you define a different rule of what function space on it means. This is more in that spirit.
Thank you.
You're welcome.
Okay, one very short question.
Yeah, I wanted to ask about what did you mean by the various components of the free-form arising in the two possible resolutions of this S1.
I just mean exactly that. Namely, first of all, there's no Lorentz invariance between element and the rest of them, because we have treated them differently. So the space, part of the definition of the compactification is the semi-nu rho behaves this way. So that's
of this as the
background.
Has this fact.
Yeah, this background means that the components of C in the internal and non-internal, one behaves in the connected resolution, the one disconnected. One important factor I did not mention, which is crucial, is that the D0 branes, when you study them, unlike the D0 branes of M theory in the context of 2A, which has higher spin fields, which gives you graviton, these KK modes have only scalars. There is no spin 2 tower. And that's consistent with the fact that they come from R plus and R minus expansions. But G nu, actually, which comes from, which is related to the fact that G nu lives on a connected space. G nu cannot live in disconnected space. It doesn't see the tower for each one individually. So there is no higher spin towers, the tower of scalars, which is very bizarre already. And this already we knew from the type 0A D0 brane structure, which was mysterious, but that's true. So we can check it from as an evidence of this picture.
Okay, so in view of time, let's pause the discussions here until the break. Thank you very much again.
Thank you.
On? Okay. Okay.
Back and forth.
Thank you.
Oh yeah.
Let's see. Yes.
Okay, so we move on with a talk by Hector Parra deFreitas about duality web for non-supersymmetric string. Please go ahead.
Okay, thank you. Okay, I also want to thank the organizers for putting together this very nice conference in this very beautiful place. And I want to also thank Kamran for introducing the ideas so beautifully that we will keep developing here. So I'm going to talk about this project with Campecar, Matilda Delgado, Emilian Dudas, and Kamran, one of the projects he mentioned. And the basic idea here is to really try to construct a non-supersymmetric duality web. So I'll just give you straight ahead what's the picture and what we will try to be understanding in detail. So as we have seen, we have a kind of M-theoretic picture of the 0A string and also an F-theoretic picture of the 0B string. Okay. And the natural question is, what can you do with that? Can you maybe construct other perturbative strings? We also saw that one of those quotients will give you a heterotic string, so I will not focus on that. And so we will see that we get unreality folds. So that's part of the talk. That's one main idea. And the second main idea is that once we have those oriented folds, we also can connect them with bosonic strings based on two conjectures that were made a long time ago in the literature by Berman Gabardil and Dudas. Dudas, Sagnotti, and so we have the BG and DMS conjectures here. So I just want to explain how this will work. So let me do that. Okay, good. So we start with this basic picture. We have a geometrization of 0A string and a 0B string from N theory and from F theory perspective. It's based on this double circle or the wedge product of two circles. Okay. And then we also have some reflections that we can do on those circles. I find it useful to keep some information here during the talk. So you can imagine that you take those two circles and you do some quotients of them, and then what can you get? And some of them should correspond to perturbative strings, as we will see. You can imagine that you take the circle, you reflect one of them, you can reflect the other, you can reflect both of them, you can put them like that. Okay, what do we get? So the point is that I talk about the reflections that give the type 0 oriented folds. Okay. The first case is the simplest. You just take the M theory compactification, you have the two circles, and you're going to reflect one of them. Okay, now, as we have seen, the doubling of the circles corresponds to a doubling of the Ramon-Ramon fields. And then one circle corresponds to the so-called plus Ramon-Ramon fields and the other to the minus Ramon-Ramon fields. If we reflect one of those circles, we would naturally expect that the corresponding Ramon-Ramon fields get projected out. Well, it turns out that that's exactly the effect of doing worksheet parity in the type 0A string. Note the type 0A string, unlike the type 2A string, it admits parity precisely because it has a doubling of the Ramon-Ramon fields. Okay. So then this is already a very strong application of this geometric picture. Moreover, in the open string sector, we also can have states because there is a tadpole. In the theory, as usual, there's a negative tension, and you can cancel it by introducing D9 branes. And so you can have two SO type groups because there are two different species of branes. And this particular combination allows you to cancel that tadpole. You could have more if you wanted, but this is a canonical choice. Okay. And it's very remarkable that I'm not going to explain that in detail here, but in the paper we offer an explanation also for how this open string sector arises from the geometric point of view by using so-called M10 branes and seeing what's the geometric action on those. So the idea here is, okay, we have an application of the geometric picture and it seems to work. So for the 0A string, there is only one oriented fold that you can do. Technically, there are more. You could also have reflected the other circle. This is just going to give you another version of the oriented fold, but it's physically equivalent. Now, we can now move on to the 0B oriented folds from an F theory perspective. We have the wedge of the two circles, and we have an extra circle. Now, here, the type 0B theory, it descends from the type 2B theory, and there the parity is like the one that we already know from the type 2B. So we naturally expect that the geometrization will correspond to a doubling of the type 1 geometry that we see in F theory. Indeed, that's actually the reasonable thing to do. So we have this quotient, this particular quotient, and we propose that this quotient describes this 0B oriented fold. But the 0B oriented fold is also special because it admits other symmetries that you can combine to get other parities and get other choices. So notably, this oriented fold, it keeps the tachyon, it doesn't do anything to the tachyon, but there's also a quantum symmetry that you can put. So as you may know, the quantum symmetry, it has to act on the twisted states of the type 0B theory, and that includes the tachyon. So this is tachyon-free, the famous tachyon-free U32 model of Sagnotti. You may attempt to have a geometric description of that, but please recall that this is geometric in a different sense. This is quantum geometry, but we still have this useful picture where when we combine the action of the quantum symmetry with the projection, instead of the two cylinders that we had before, you can think that they cap off, the two circles are identified at the edges because the quantum symmetry identifies those two circles. So you have this funny geometry. And so we also have an explanation for this model coming from the geometric actions. And finally, there's a theory default that you can do that it's a bit ill-behaved, but still is well-defined as a perturbative string. And you can then combine the reflection on the base circle here with the full reflection or the reflection of the two circles here. And you get like two pillows that are sewn together here at this seam. I didn't mention in the type 0A that you could also do a reflection of both circles, but that's not very interesting because if you do that, you just get an interval, and that would correspond to the very well-known for Java Weigand construction. Okay. So these are the orientifals. Good. And now we're going to focus on one of those, of the 0B, which is relevant for connecting with the bosonic string. In that theory, you also have a massless tadpole, you also have a negative tension, and you can introduce branes to cancel them. And you can introduce branes of either of the two species because the Ramon sector is doubled. But there is a special case where n is equal to 0, where you don't have fermions in the spectrum. And just to clarify on that point, in the spectrum of the type 0 strings, when you have branes, if you have two branes that are of different species, and say this is dp minus and say this is dp plus, okay, and you look at the open string structure between them, those are going to be fermionic. If they go to themselves, it's going to be bosonic, okay? And then if you have anti-branes, you get tachyons. But precisely in the case where you only have one species of branes, then you don't have fermions. That's very interesting. Because then it makes plausible the idea that this could be dual to the bosonic string. So this was indeed proposed by Berman and Gabardiel. And there's more evidence. It's not only this fact, it's also when you look at the spectrum of the tachyons, here you have branes and you also have anti-branes. So the actual configuration that you have is, for example, dp plus plus, dp plus, and dp plus bar. So you get tachyons. And so in this particular case, you're going to have tachyons in the fundamental representation of the gauge group. Okay. And that's also something that you see in a bosonic string. So to be concrete, if you take the bosonic string, which is 26-dimensional, and you compactify it on a T16, you get a 10-dimensional theory. There's a special point in the moduli space, in the Narain moduli space, where the gauge group is SO32 times SO32. Actually, there are two of them. This was not noted by Berkman and Gabriel. There are two different points, but it's only one of them that actually corresponds to this duality. It's given by a polarization of the Narain lattice, if you're interested. Okay. When we look at this specific point, we see that many fields match. The metric matches, well, that's reasonable. You have a dilaton, the gauge fields are the same. You have a singlet tachyon, although that might be a bit misleading, as will become clear now. And you also have the fundamental tachyon. Still, there are some apparent mismatches. So on the bosonic side, this is a compactification. So you have Narain moduli, and those sit in the B adjoint of the SO32 times SO32. You don't see those in the 0B construction. Okay, so that's one apparent puzzle. And the second one is that in the 0B side, when we quotient by omega, we do not get rid of the doubling of the Raman-Raman fields. We have still two B fields. So, okay, that doesn't make sense from a bosonic perspective, from a bosonic string perspective. So these puzzles were there in the Berman-Gavardier paper, and especially the second one was not resolved. There's another striking piece of evidence, which is maybe the most important. When you are trying to examine a duality between two string theories, one of the most useful tests is to look for the dual string as a solitonic string in your theory. If you look at the D1 plus, and in this case, let's just say this was actually minus. If you look at the D1 plus, sorry, the D1 minus of that, sorry, the D1 plus of that theory, the strings that go from this brain to this brain, as I said, they give you fermions. And the strings that go from the D1 to itself, they give transverse scalars as usual. But the fermions are very important because you have brains and anti-brains. And so some of the brains are giving you chiral fermions of one chirality and the other of the other chirality. So in the end, what you get is actually exactly the content of the worldsheet of the bosonic string in the quantification of SO32 to SO32. Okay, so that's a perfect match. Okay. Therefore, the D1 plus is a fundamental bosonic string. So that's not under any kind of doubt. This is a fact. This is a fundamental bosonic string. So then, how is it that we can solve those puzzles? The first puzzle is not really that complicated. There are indeed massless scalars at tree level, but and you don't see them in the 0B, but actually we already know from many decades ago of work of Parra and Vafa in the context of the non-supersymmetric heterotic string, but actually this applies generally, is that those massless scalars are generically going to get masked because you have a non-zero potential, non-zero correction to the potential from one loop already. So there's absolutely no reason to expect that those should appear. There is a worry that they could become tachyonic or something like that, and we don't really have control over that. You would need to have some kind of non-perturbative statement. But again, there's no reason to expect that they should be there. And also, because you have the enhanced symmetry, that already means that you are at an extreme. So this statement of the behavior of the massless moduli applies particular to these enhanced points. Okay. So it's not like running or something like that. The second puzzle is more worrying and more strange. So you have two B fields. One of them is coupling to the fundamental string. That's the one that you expect to keep. Okay, but you also have the other B field. It corresponds to some D1 minus brain that you have somewhere. Say. Okay. And of course, there's no perturbative counterpart for the B minus. Before I show you the mechanism, need to emphasize that you need a mechanism for getting rid of this, and what you could naturally think of is maybe you can Higgs it, maybe you can Higgs the B field. Okay. So from supersymmetric theory, we already know that there exists that kind of mechanism to do that. So I'm going to explain that, but there is motivation to expect that such a thing can exist here in the supersymmetric case. As Cameron was explaining towards the end of his talk, there is a conjecture for how the tension of the difference changes. So why is that important? Because if you were able to get a tensionless difference, particular if you were able to make this difference tensionless, then you could hope to have a Higgsing mechanism for the B field. That motivates looking at how the tensions behave. If you look at the quotient of the tension of the D1 minus and the D1 plus, this is going to be something like the square root of, let's say, 1 minus t and 1 plus t, up to a convention of the signs. Yes. And you can make this diverge by suitably choosing, for example, here t to be equal to -1. So if you want to establish this duality, this is already telling you something extremely important. It's telling you that it's not enough, as was believed in, or as one could be led to believe from the supersymmetric setting, that, sorry, there's no water. From the supersymmetric setting, that you assume the coupling. It's a strong weak duality. No, but if you actually want to make sense of this, you need to tune the tachyon. So you're kind of treating the tachyon as a modulus and thinking more broadly of coupling and the tachyon. So in this picture here, you can imagine that this is the, thank you. The bosonic string here, and this is the type 0 string, and this is the potential as a function of the tachyon expectation value. So you are sitting here, and you want to find a way to connect it to this point here. But what does this mean? T0 here is just the expectation value of the tachyon from the type 0 frame. As you tune that and you go to, say, -1, depending on conventions, you you arrive at this point here, where now the D1 brane becomes tensionless. And then you can Higgs the B field. This is analogous to, in the supersymmetric setting, to having a tensor branch and a Higgs branch. So, so that you can Higgs the B field and then move on to a kind of a Higgs branch. Here we're also implicitly tuning the coupling. And then there's some phase transition here, from where then you can then tune the tachyon of the types of the bosonic string and move back to that maximum of the potential that characterizes the perturbative bosonic string. So this is the proposal that we have. There's something along these lines has to work. This is, of course, very speculative for many reasons. One of the reasons is that the formula of García and company is conjectural. We don't know if there are corrections to that, but it's remarkable the fact that just assuming that it gives us exactly what we need to make sense of this. So the tachyon condensation is part of the duality map here. With this, we resolve this puzzle. I can say also that there are other interesting coincidences, like you have the tachyons coming from the open string sector in the type 0 string, and those coincide with the tachyons in the worldsheet of the bosonic string. You can think about tachyon condensation on both sides, and that will give you critical strength. So there are other pieces of evidence, but still this part here is not really understood how this Higgsing could actually work. How does this look like? How does it look at this point model space? So this is very interesting question to pursue. Then finally, something very funny is that you could then go back to the type 0 identifiable, and you can buy more things with that picture. Because what we're proposing here, when we have this description of the type 0 identifiable, is that, okay, this is a geometrization. Can you do something more with it? Well, Carmen told us that we can think of the tacking also here as a geometrized object, namely the difference of the radii of these two objects is corresponding to the tacking. So you can think about tacking condensation. Okay, and as we have seen, also, tacking condensation is related to S-duality. Now, dudas Murasagnotti conjecture based on an analysis of the theory of omega that a particular configuration where you have the branes here, so you have an SO32 here. Okay. The spectrum of the theory actually corresponds to the spectrum of a bosonic orientifold. Okay. And so then a strong coupling maybe you also have a bosonic string, so they are inspired by Bergman and Gabriel, and you have the same kind of puzzles. You have Nari moduli. What do you do with those? That's not a problem, as we have seen. And in the 0A side, you have the extra Ramon fields, the A plus and the C plus. This is actually easier to deal with because we can think of doing just stacking condensation, get rid of the circle, shrink it, and then you get rid of the Ramon fields. Okay, so then this duality is perfectly explained. Moreover, you could think intuitively that this is orientifolded version of the Bergman-Gabriel conjecture. So if these two things hang together, then that's even more evidence for these dualities. So just to summarize, what's the takeaway here? We have this new geometric picture for the 0A and 0B theories. How far can we take those pictures? We can organize the landscape of non-supersymmetric strings using them, maybe. And we can then come back to all the proposed dualities and use these ideas to get more insight into those and push them further. Okay. And also that we can geometrize the tachyons and we can use them to move in moduli space, and they really play an important role here in strong-weak duality. So that's what I wanted to say.
Thank you very much for a very nice talk. We have time for questions.
Thanks for a nice talk, Hector. So I wanted to ask, for the type 0, there's just fermions on d-brane warp volumes, correct? Even though they're not in the perturbative spectrum. Does that imply that we also have fermions in non-perturbative spectrum in bosonics through the duality, or?
Sorry, you have fermions where in the type 0?
I thought maybe I'm wrong. I thought that was the case.
But you said in
the d-brane spectrum. Was that right? So not at the massless level.
If you include branes on top of the background, then you might have fermions, and you can ask.
Yeah.
Yes, but we didn't think too much about that. I know they're having papers considering the possibility of having fermions in the bosonic string, but as far as I could check, there's no real match here. So that remains.
There's a question over there.
I have a question about the puzzle one, also with the bosonic string with the matching of moduli. So the argument is they maybe get a positive mass, and that's how you match. However, in your paper, I think you showed that there is a computation that you can do on one of these sites that tells you that this mass that they seem to pick at the perturbative level has the wrong sign and it's negative.
Yes.
I wanted to ask if there is any independent argument why this mass will eventually actually be positive.
Independent argument, no. The argument that should happen is because we would trust that the duality works. So duality would require that, but I don't know higher loop compositions, things like that.
Are there more questions? If not, oh, there's one there. Really get some exercise.
Is there any picture of what happens if you have more than two SVS, something like a SVS, or maybe in a line, or maybe connected three in like a sort of triangle?
Not that I know of. Oh, well, we have,
I guess,
maybe some use.
There actually is a hint. So zero, I didn't get a chance to say, but 0A and 0B, I said they have the moduli space. So 0A has the string coupling and the tachyon. It turns out you can also view it as a moduli space of flat SU2 connection on a circle. Well, namely the circle size. And tachyon, as you saw, has a web which goes between plus and minus 1. So which is the SU2 holonomy, which is S1 mod Z2. So in other words, the moduli space of 0A is the moduli space of SU2 flat connection on a circle. And the moduli space of 0B is also the moduli space of SU2 flat connection on T2. So the tau and the Z, you can interpret it as a flat SU2 connection. It is as if, even though it's a bizarre statement, it's as if you take two copies of the universe and put them together like in D branes and talk about flat connections. So therefore, I would imagine that the answer to your question, it can have more copies. The analog would be yes. The analog would be SUN flat connection would be the moduli. And why I wouldn't know, but it sounds like it's natural extrapolation from it. So it should make sense to talk about more. And naturally, I would go with the AD, at least as an interesting possibility for putting universes together as a disconnected kind of almost touching at some point. So that's the picture I would think is possibly true. It'd be very interesting to see if this is correct picture, bring it to life.
Hi, Hector. One quick question. Do you have a proposal for how the Sugimoto string would fit in this kind of geometric construction or semi-geometric?
No, that's a very good question. We didn't, or let's say we intentionally did not think about the symplectic projections. So, no idea how this would live geometrically.
Okay, so with that, let's thank Hector again for a very nice talk. And we will break for lunch and reconvene at 2.
So I don't know, is it on? Yeah, it's on. So I hear myself.
Hello, everybody. Welcome back. We start this afternoon session with a talk by Miriam Cvetic about symmetry theories, anomalies, and data invariance. Please, Miriam.
Well, thank you. Thank you to the organizers for organizing such a wonderful meeting here and the opportunity for me to come back to Uppsala. So what I'm going to talk about is part of a broader program at Penn, where we try to address higher symmetry structures from string theory. And in the recent work, we are focusing on more refined data, such as anomalies, and how they can be expressed in terms of so-called eta invariance. The work will have two parts because a somewhat older, less recent approach is using to discuss those properties by using geometric engineering in string theory. And in the second part, I'll highlight the most recent work where we are employing for studies of these features quiver approach. Oops. I thought, yeah, sorry about this. Escape. Should I escape? Oops, now I escaped. Okay, it's working now. Let's hope it continues like this. Anyway, this work is based on recent work for studying geometric engineering data, work with Rondonaghi, John Heckman at Penn, and Max Hübner, who was at Penn, now at Uppsala. And then the most recent work, really about to appear, with a student at Penn, Vivek Chakrabarti, John Heckman again, and Shani Maynard, who is at Penn, but he came from Uppsala. So some of the work is also based on earlier work, primarily employing techniques of geometric engineering. So first motivation for using geometric engineering to study higher symmetry structure, that is, of course, quite natural and well-established approach where we study string theory on non-compact singular spaces. And then the way we address calculations for symmetry, in particular for symmetry structure, is really resolving the singular geometry using intersection theories and other methods to compute the desired quantities. And that has been done to great computational success. However, we expect that in particular for studies of higher symmetries, those quantities are often topological. So calculations are expected to be possible also in singular spaces by employing algebraic or differential topology. There may also be cases where the singular geometry is too complex or we cannot resolve it. And so we would have to study such features directly in singular geometry. Some progress has been made actually in those directions by deriving those properties of higher symmetry structures directly in singular limits. One example is the example of nested or non-isolated singularities in geometric engineering. Also some recent work on frozen singularities, interesting work, potential work directly in the case of terminal singularities, and studies also of non-supersymmetric string examples. Again, some of the results in this field have been obtained by employing algebraic and differential geometry, and at the same time also contributing to a toolbox in these subfields. So the second part would be motivation for studying quiver approaches in addressing higher symmetry structures. One should say that this is much less explored subject. One would anticipate in this context that this data could possibly be obtained directly from the quiver data by studying path algebra of branes that probe these singular spaces. Some of the progress in this direction, in particular to study defect groups directly from quiver theory, has been obtained by a number of recent authors, in particular also people that are here at Uppsala. So the hope is that we can advance these approaches by using quiver data complementary algebraic approach, which is, of course, complementary to geometric engineering. So the outline of my talk is the following. First, the geometric engineering approach. First, the origin of defects, operators, and symmetry field theories in geometric engineering is well established in the recent years. And so I will also primarily focus on anomaly terms in symmetry, TFT symmetry theories via geometric engineering computation of anomaly coefficients, namely more refined data in this context. On the quiver approach, I will briefly present a procedure to extract the higher symmetry structures, but in particular, already symmetry TFT anomaly coefficients by directly probing singular space by brains whose quiver data of corresponding quantum field theory probes such singular geometry. So it's the quiver data that will give us these results. So in the rest of my talk, I'll take a particular prototype of studying quantum field theories from string theory. Namely, I'll choose M theory, and the non-compact space will be non-compact conical Calabi-Yau threefold. Actually, concrete prototype that I'm going to use will be orbifolds of C3 mod finite subgroup of SU3. So a well-known story, the global symmetry in quantum field theory are introduced via non-dynamical extended defects like Wilson lines for one-form symmetry and the corresponding operators acting on them. The zero symmetries, of course, are point defects and corresponding gauge symmetry acting on them. It is potentially interesting that we can deal with interplay of zero and one-form symmetries, which could lead to two-group symmetry and non-invertible ones as well. So to apply this idea of higher symmetries, defects and operators in geometric engineering is very natural. Namely, we choose the extra dimension to be associated with non-compact space, singular space. In this case, I'm going to choose non-compact conical space where we would put isolated singularities at the tip of the cone, and that's the one that would then fix the physical degrees of freedom of the resulting quantum field theories. Now, the appearance of global defects in resulting theory are associated now with branes wrapping also non-compact cycles in extra dimensions, and the corresponding operators of higher symmetries, symmetry operators, will be associated in extra dimensions with branes wrapping cycles on the boundary. So in particular, in M theory, electric defects are associated with M2 branes wrapping specific cycles that are specified by relative cohomologies, and the magnetic ones, the corresponding complementary relative cohomologies of M5 branes. The operators that act on these defects correspondingly are associated with specific homologies on the boundary. So again, I'm going to primarily highlight things with one-form symmetries, which in this context will be associated with P1 defects, lines, Wilson lines, and associated with M2 branes, wrapping non-compact cycles. So symmetry theories appear when we try to study actually further data about representations, also whether the symmetry, how they are represented, are they spontaneously broken or not, and further data that is associated with the symmetries like anomalies, etc., can be packaged in terms of extending the original quantum field theory to one dimension higher and refer to this as a symmetry topological field theory. In particular, on one side of this quantum field theory, physical degrees of freedom in this extra dimension are on one border, and the typical topological ones are on the other border. And often some questions that we want to address in this TFTs may depend just really on the boundaries, topological boundaries. So in geometric engineering, obtaining SIM-TFT is again very natural. In particular, we have this extra space, and if in the case of conical space with isolated singularity, say, that quantifies physical degrees of freedom of the resulting quantum field theory. If we compactify on the compactification of the boundary over this radial slice, we would obtain naturally the description of a theory where this extra dimension, this extra radial slice, specifies the extension of SIMTFT. On one side, physical conditions associated with the singularity. On the other side, we are dealing with topological boundary conditions which are governed in M theory via supergravity. Now, it turns out that we can have in general, more general singularities in extra space. So in the case of non-isolated singularities, SIMTFTs seem to be more, have more complex structure. And in particular, as we go directly just to quantum field theory, the nested SIMTFT has a typical prototype where we start with the quantum field theory in bigger dimension, and we insert a dynamic defect, quantum field theory associated on dimensions smaller than the big quantum field theory, so inserting the defect. And this combined system has now the more complicated SIMTFT, namely referred to often as sandwich, where we can actually extract key features of the SIMTFT by compactified bigger dimensional quantum field theory to just one dimension higher than the lower dimensional one. So this now becomes just lower dimensional defect quantum field theory, and that would the effect of physical higher dimensional quantum field theory. And the corresponding SIMTFT is now associated with the bulk contribution of bigger quantum field theory and the boundary contribution of SIMTFT associated with the defect quantum field theory. So we often want to understand data that come in such nested SIMTFT, the way they appear on this extra direction of the boundary SIMTFT. In any case, this is old story. Let me just emphasize that within geometric engineering, this is again very natural, as I was already alluding to, is that those are associated with non-isolating singularities, namely what ordinary SIMTFT is to isolated singularity, nested SIMTFT is to non-isolated singularities, which we observed about 2 years ago, and with other further extended work that followed. So the prototype that would generate such nested SIMTFT in geometric engineering is again an example of orbifold, which is a particular cone of S5 mod gamma. And in this orbifold, in addition to codimension 6 singularities, we also have flavor branes associated with codimension 4 singularities that extend all the way to the boundary. And those loci are associated with a C2 mod, another subgroup, smaller subgroup Fx. An example prototype is the Z2N orbifold. In particular, it has codimension 6 singularity at the tip, but there's codimension 4 singularity associated with locus C2 mod Z2. And as a consequence, in this case, we describe now the tip generates 5-dimensional conformal field theory. And then we have also now flavor brane associated with this extension. And we can view the system as a combined system of SUN 5DCFT defect that is nested in 7-dimensional flavor, so SU2 super Young Mills. And with this geometric engineering in the past of such examples, we were able to study directly identifying geometric origin of higher symmetries, namely studying the symmetry defects associated with one form symmetry and interplay with 0 form symmetry that results in 2 groups. by really using this singular geometry, cutting and gluing singular boundaries of the non-compact space and employing the so-called Meyer-Virtoris sequences to identify the defect groups of that type. Subsequently, we also constructed nested CMTFT that results from this joint 5D, 7D system and reproduce not only the whole symmetry defect group structure, but also generalizing, in particular, the effects, what happens when the bulk CMT, DFT, and its boundary conditions imposing by the boundary CFT constrain the type of operators we can have in this theory. In any case, this is somehow older story. More recent story is to refine the study of CMTFT by studying coupling, anomaly couplings, and I'm going to focus really on this at most boundary CMTFT, which we are describing now as a 5-dimensional quantum field theory on an interval where we compactify on 6-dimensional space, not on non-compact space. And the starting point for this anomaly calculation is 11-dimensional supergravity, the well-known term that involves 3-form gauge potential and geometric pieces associated with A-form classes. And to make it globally defined, we extend it to 1 dimension extra. And this is the well-known Chern-Simons action in 12 dimensions. To get the symmetry theory on this interval arising from this topological term, we have to reduce the Chern-Simons term on a 6-dimensional space and obtain CMTFT action in a 5-dimensional space clustering interval. Now, this 6-dimensional space need not be the original X as long as the boundary of this new space is the same as the old space due to topology. And it's from this action that we reduce now the pieces that are associated in particular case of orbifolds. Again, we want to focus on 1-form symmetry, so we are reducing the 4-form potential via internal to form field strengths that sit free classes of second cohomology and obtain the pieces that are associated with self-anomaly of this B2 fields and actually mixed gravitational anomaly. And there's coefficients beta and gamma are associated with F3 square and F2 pieces and some geometric pieces integrated over 6-dimensional space. So it's this coefficients that we want to get. And we see that to get these coefficients in particular, we can get the sum of those coefficients by studying the Atiyah-Padodi-Singer Dirac operator on X prime with an extra line bundle whose first Chern class is F2. So the Dirac index on this space involves the bulk contribution we can identify precisely with the sum of this coefficient beta and gamma, and the boundary pieces that involve the kernel of the Dirac operator on boundary, which in this case is 0, and very importantly, the spectral invariant of Dirac operator twisted by this line bundle on the boundary. And it's this guy that will be crucial. Since this index is integer, the first part is our alpha, the second part is eta invariant on the boundary. And also boundary is the same, also in the singular space. So we see that alpha, combination of beta and alpha, is related precisely by the eta invariant of this Dirac operator twisted by L. And its calculation of this term now in singular geometry that can determine for us anomaly coefficients directly. And mathematicians have done that for isolated singularity orbifolds. There is this beautiful formula that gives us this alpha precisely expressed in terms of shifts of the phases of 2 pi I over n. Now we can confront that with all calculations when one did resolution, one did intersection calculations and obtained alpha. In the bulk, our calculation involves this piece, and of course they agree. And for example of this isolated singular orbifolds is well-defined formula, which now matches to the old calculations. Now for we can also split that into beta and alpha by scaling the charge of the particular representation, which also allows us to rewrite beta and gamma in terms of eta invariance for line bundles where the charge is chosen to be twice the original one and the original one. In any case, we are done. We can get this anomaly coefficients for all the isolated classes of orbifolds, isolated singularity orbifolds. I'm running out of time. I'm pretty eager to still say a few things about quiver. So in the case of non-isolated singularities, things are a bit subtler, but we can again, the result is still the same, is calculating eta invariance of this Dirac operator with the twisted biline bundles. Correspondingly, it happens that actually even in the intersection theory, looking at some special examples, one did have example of that type of geometry resolved and calculated. Indirectly in field theory, that example seemed to be also introduced, and anomaly coefficients agree. And now we have this calculation, and they also agree. So for this case, I have to emphasize that in this case, the eta invariance does not take examples where we are dealing with fixed plane. So only examples where we have isolated singularities, where we sum over and get the correct eta invariance. And other examples of single parameter space with isolated singularities, calculations for even non-abelian and Cronzian. So that's all based on, we could do that because mathematicians had done calculations for us. Now, if you give me 5 minutes, I will just highlight few things from the quiver theory. Last but not least, okay, for non-isolated singularities, we also found that there are further terms associated with anomalies, which I didn't highlight there, but they are associated with this flavor symmetries associated with branes extended to infinity, and this mixed flavor brane anomalies were also identified early on. Okay, quivers. Now we want to address the same type of geometries, but using quiver theories. Namely, we want to, we would like to probe these things by, for example, in type 2A, by realizing quiver quantum mechanics by compactify on S1, and D0 probe, resulting D0 probes the quiver quantum mechanics, or T-dual picture type 2B with D3 brane probing the same geometry. Its quiver is realizing the D equal 1 and equal 1 theory. So let me point out that this eta invariant, that's for the Dirac operator that is not twisted by line bundle, but for chosen parametrization can be calculated in that way by, again, using elements that are in the subset acting a fixed point freely on the sphere. That's actually more general, the Garato result. What he has proven for us is that the same result can be obtained as a residuum of this expression, where the residuum is governed by the twisted Moulin series. Moulin series now actually is an expression that that counts, is a generating function that counts the number of certain holomorphic invariants, certain invariant polynomials of particular degree. And in this case, it's also twisted by this representation, twisted by finite group action. So this is another way of writing eta invariance for untwisted Dirac operator. Now, the twisted one that we are dealing with is actually the difference of the eta variance for line untwisted Dirac operator for line bundle L, and the one without, with the trivial one. So that means this now becomes, in terms of the Garato, that our eta invariance is the difference of this residuum where we have the difference of in the numerator of twisted Moulin series and the untwisted one. So this is well known, this counting is well known. So we are getting now from geometric engineering to representation theory. And for Z3, this is well known, you calculate and you get the well known result. Okay, now how do we go to the whole series for all the other examples? And how do we go really to quiver theory? So for that purpose, we generalize this Moulin series to Hilbert series that is matrix valued and is actually refinement of Moulin series. And it has particular properties that the ijth element of this matrix valued Hilbert series is dealing counts for us, classes of paths from quiver node I to quiver node j. And I equal j, we are dealing now with the loops. I not equal j, we are dealing now counting this interpolation between this distinct fractional brane using actually particular orbifolds that I want to show results and choosing irreducible representations of gamma and representation of gamma on C3. We can introduce Mackay adjacency matrix through this relationship, which gives us now in this case, much simpler form of this Hilbert series. And that's of that form in terms of adjacency matrix. And here we can now read off different elements. H00 element is precisely untwisted Moulin series. J01, 0I is precisely the twisted Moulin series that I introduced earlier. And so anomaly coefficients is expressed in terms of difference of the residua of this H00 and H01 matrix element of the matrix Hilbert series. So this is actually now completely from quiver theory, and H00 we know counts H invariant operators, H01 counts twisted operators in this case. Completely calculable results. We can do it for Z3, get adjacency matrix, get Hilbert series, matrix valued one, and get this result. Final remarks, 30 seconds. From this perspective, now the way we connected now to really the anomaly coefficients directly to quiver data of Hilbert matrix value Hilbert series allows us to generalize that from isolated singularities also to non-isolated singularities. Examples of all the orbifolds with non-isolated singularities can be precisely calculated. It's subtle. I don't have time to go into it. We also are beyond the orbifold things because mathematicians, De Garata et al., they calculated this theta invariance for us, okay? We are just applying it. Now we can use quiver theory for examples of cones over LPQ or LPQR and use really complete quiver data analysis to get eta invariance, namely this anomaly coefficients for cones. In particular, explicitly for cones YPQ, subtle, we have a number of results for that, including multi-parameter examples. This is trickier because, anyway, last 10 seconds, okay? We also found for 9 isolated singularities more refined data for anomalies, which has to do precisely with this flavor global symmetry and the mixed anomaly there. And this refined data captures for us actually this anomaly that does not involve only pole at 1 minus 1 Laurent expansion, but also at the 1 minus 1 to the second power Laurent expansion. And this is the refined anomaly that is related to beta gamma, and now this mixed flavor brane and directly flavor brane anomalies as well. Thank you.
Thank you very much,
Thank you.
Miriam. We have time for a couple of quick questions.
Thanks for a nice talk.
Thank
so
you.
probably this question is not relevant for you, but I'm just curious. if you applied mirror symmetry to these, you get a different description. Would your calculation be any easier or harder in the other side?
So from type 2A to type 2B?
Yeah.
For the squiver calculations?
Yeah.
Possible, but you're expert on these techniques.
Well, the residue formulas reminds me of
Yes.
holomorphic structures of a mirror, which is why I'm asking.
I see.
I would have thought that might be easier. I don't know. I mean,
Right.
the mirror techniques are easily applicable to these local singularities. I'm just
Right.
curious. For example, like when we did non-supersymmetric orbifolds, the most powerful method is mirror symmetry. So I'm just wondering
Indeed.
what happens here.
I think this is very good idea. That's also, another part that I highlighted, non-supersymmetric examples as well. Indeed. And now it's all, representation algebraic thing. Yeah. Thank you.
Hi, Miriam. Yeah, thank you. This was very nice.
Thank you.
I had a very simple question. So everywhere you considered gamma inside of SU3 orbifolds, but I didn't see where you used n=1 supersymmetry anywhere. So could you extend to quivers from gamma inside of SO6? So n=0 quivers? Did anything go wrong? Anything is not protected?
You mean on a geometric engineering side? Geometric engineering, that's quite possible. Actually, mathematicians again looked at these examples, right?
Right.
As well, so it need not be. Here is not clear. Quivers are very asymmetric. It's very hard, but maybe Jonathan can say something. Yeah.
Yeah, so if I understand your question correctly, if you do an SO6 subgroup instead, and then you look at the non-supersymmetric ones, the issue is that those often have they have a twisted sector tachyon, which will cause the singularity to start blowing up, or part of the singularity at least to start resolving. So from the SIM-TFT point of view, what it looks like is there will actually be an interface between what will look like one SIM-TFT and then another one, and the other one will kind of be a moving shell that moves outwards to its infinity. And then if you go all the way out to, if you like, Scri+, so you have to consider the time dependence as well, then you'll see a bordism between like one orbifold and another as it jumps because of the resolution of the singularity.
That's what you studied with Max and
That's
company,
right, yeah.
yes.
So perhaps, yeah, in the interest of time.
Okay.
Won't
Indeed, there are lots of open things to
Nice.
pursue. Thank you.
Nice. So just thank Miriam again.
Thank you very much.
Thank you very much.
Thank you. Just 25 minutes, huh?
So now we continue with Iñaki García Etxebarria, talking about anomalies and vanishing of partition functions.
Right. Thank you very much. Thank you very much to the organizers for putting together the workshop. It's been super interesting so far. And thanks for giving me the chance to present this work that I did a few months ago with my student Felix Christensen and Enoch Leon, who is going to join us in Durham soon. And the work is about trying to understand certain vanishing of partition functions using modern ideas about anomalies and SIM-TFTs. So ideas that Miriam reviewed recently. The motivation was, in a way, quite technical, but I think the results are quite general. So the original question came from something we encountered in this paper with Muldrow, who is somewhere, I think, in this room, and Ben and Sebastian. And we're looking at some brains on S-folds, so some very non-perturbative backgrounds. And we needed for the whole picture to be consistent, to apply some generalization of the Friedwitten anomalies in this background. So if you don't know what these are, if you have a D brane on some background, perturbative type 2 background, say, and you have some B field, if you compute the restriction of the B field to the over volume of the brane, it has to obey some conditions. So the class of the field strength of the B field restricted to the brane, plus some characteristic class that depends on the geometry of the cycle where the brane is wrapped, has to be 0 in cohomology. So the original derivation by Weigand was a wall-sheet derivation. It applies to type 2 with coupling, but the systems that we had at hand were not of that type. We couldn't find a duality frame in which these things were perturbative. So we just didn't know what to do. We conjectured the answer. There was one answer that made the whole picture hang together. It's probably the right one, but we couldn't prove it. So, all right. That was the status, but then we kept thinking out this. It was a bit of a bother because the whole picture sort of relied on some generalization of this thing to be true, and we don't know how to start proving this. So what I want to describe today is a way of rethinking what this condition means in a way that you can actually extend it to many backgrounds, non-perturbative and so on. So entirely different derivation that applies much more broadly. And the point of view I will advocate is the following one. So let me forget about this W3. It can be included. It has to do with fermions, but let me forget about it for a second. You forget about the fermions on a D brane. What you have is Maxwell theory, supersymmetrized and so on, but you essentially have Maxwell theory on some manifold, right? And from the modern point of view, what B2 is doing, the restriction of the bulk B2 field, we now speak of this as a background for the one-form symmetry, electric one-form symmetry of Maxwell theory. So translating to a word that we would say now in SymTFT or symmetry language would be that we require that we have Maxwell on some form manifold, and you have some non-trivial background for the electric one-form symmetry. Its field strength has to be trivial in cohomology. In other words, the background for the electric one-form symmetry of the Maxwell theory on the brane must be a collection on a trivial bundle. It is just a translation of what Weigand said. Now, the key point here is realizing that something that sounds, we say all the time, but I realized I didn't understand it very well, which is this word must here. Okay, must, what happens if you don't satisfy this condition? Does the world explode or what? I don't know. So the answer was given, in fact, in this super nice paper by Sieta, Chikawa, and Yonekura a few years ago. They do many, many interesting things in this paper, but one of the things they do is they give sort of a constructive answer to this question. They say, well, imagine you have Maxwell theory, right? And if you put one of these backgrounds in which the characteristic class of the background for the electric one-form symmetry is non-zero, then the way you should think of this is that you can do this, but your partition function will vanish. The partition function of this theory will be 0. And I suppose many years ago, this was a bit more of a problem. You would think, well, if the partition function is 0, the theory doesn't make sense. But now, 0 partition functions appear all the time. When we think on non-invertible symmetries in many sectors, this is what they do. They just vanish for some sectors and they don't vanish for others. That's why they are non-invertible, because 0 doesn't have an inverse. So that's the first idea. They told us that no, you can include these things, but if you do, the partition function should vanish. And the second thing they pointed out in some restricted example was that you can understand this vanishing from anomalies. Now, the technique that we used in the paper was quite different from what they say in the end. Much more computable, much more general, but they already point this out. So now you put these two things together and you realize that, well, maybe if I know the anomaly from my quantum field theory, this complicated as full story, the theory itself is complicated, but I know the anomaly is pretty well. So if I can recast this vanishing of the partition function as a consequence of having certain types of anomalies, I can generalize what Weigand was saying to many non-perturbative backgrounds. So that's what we did. Okay, so that's the main idea of the paper. What I'm going to do now, and it's very unlikely I will reach the end. So what I will do in this bit at least is try to motivate the main idea here, and then the paper you can read the details if you want, or the more complicated calculations that we did. Okay, so let me review something which is super basic, but just to set the stage to make all this thing much less mysterious. So consider the case of a free Dirac fermion in 4 dimensions on some closed form manifold. So it has 2 symmetries, 0 form symmetries, an axial one and a vector one. Written here, they have already appeared in the conference. And there's a mixed anomaly, in this case a Toft anomaly. I'm not gauging the vector or the axial, these are just backgrounds still. But these currents that I could write, this one in particular, the axial is not conserved by this quantity. If this is not familiar, think of this as F vector squared, the instanton number, the local instanton density, I should say. So to write this, I'm setting the axial background to 0, it just simplifies things. And there's a pesky factor of 2 because the Dirac fermion is like 2 vials. So I have redefined my axial current to absorb this factor of 2. And that's just because yesterday night I was getting factor of 2 wrong when I was preparing the slides, and I decided to redefine it away. Anyway, so that's what I have. I have this non-conservation. So the way to understand this equation, this is very familiar stuff, is that, well, I'm still integrating over the fermion, and the fermion appears in the current. So this, what it does is there's a modified word identity in the path integral. That is, if I encounter a dj in my path integral, when I integrate in the fermion, I can replace it by this combination of background fields. Okay, all very standard. So I want to consider this operator, the integral over the whole 4 manifold of the divergence that doesn't vanish. Because of Stokes and the fact that this manifold by assumption, I'm taking it to be closed, this has no boundary, this thing has to be 0. All right. But now we have the modified identity, the García identity. So I compute this in a different way. I take this Q, this integral of the J. I replace the J, the divergence of the J by this index density, this combination here, and I get a particular combination, which is this integral of this A hat term character with times the partition function. So we learned that the partition function, this factor here, which was the integral of the fermion with direction in this given background, times this integral here has to be 0. All right. Of course, this seems to be a bit of a funny situation, but of course, what saves the day is that the thing that we got here was the index, as is familiar to most people in this room, I guess. And what you have is that the index, the difference between the right-handed and left-handed 0 modes of the Dirac fermion is given by this integral over the manifold. So what we found is that the index times the partition function has to vanish. And that's true because whenever the index is non-zero, we do have a 0 mode. A fermionic 0 mode in the path integral will kill your path integral. Whenever this thing is 0, then there's no reason for set to vanish, and that's fine because 0 times anything can still be 0. This is, of course, very elementary, but it sort of motivates, I think, that this vanishing has something to do with anomalies. So I want to go in the direction where I don't have a path integral formulation. I want to formulate everything in terms of anomalies. So let's see. Let's think about this divergence again. The divergence equal to F squared, if you want. One way of understanding this equation is saying that whenever I have this thing on the right different from 0, this combination of background fields different from 0, F squared different from 0, I'm introducing charge under the axial symmetry. So the backgrounds are charged under their axial symmetry. And then this integral is telling me how much charge I'm introducing in my 4 manifold. So the conclusion that whenever this integral is different from 0, the partition function should vanish. It can be rephrased as saying that whenever you have net charge on your closed manifold, the partition function must vanish. This is starting to be a bit more actionable. And the argument here is, I think, I don't know, when I talk to people, sometimes some people don't know this argument. It's fairly standard, but I don't know if everybody knows it to review it. The proof is quite easy. So imagine that you have some current which is conserved away from operator insertion. So you have some O's, a carry charge. I put them at some points, x1 to xk. And then dj, the current is conserved away from the operators, which are inserted at these points, and each one carries a charge. Right? So if because I have this identity, the operator that I construct, the current is topological away from operator insertion. So I have I deform the operator a little bit. I have the operator sigma, operator sigma prime, these two ones. I compare them, that is multiply one with the inverse. I get the integral of j over the difference. Use Stokes, I get the integral of dj. If there are no operators in here, dj is 0, so this is 1. This is a standard argument for operators being topological. If I do have an operator, when I do that, then dj picks one of these deltas here. And then I get the charge of that operator in there. So this is how topological operators see charge insertions. So now, why do partition functions or these kind of correlators with net charge vanish? Well, one argument is the following one. Imagine that you start computing, this is a bit schematic. What I mean is the partition function with insertions of operators at certain points. I draw just one, so a bit something like this, but with just one point here. This is the partition function of this correlator that I want to compute. What do? Well, this is equal by nucleating a little symmetry operator around the point. Because the operator is topological, I can nucleate an operator here, topological operator. These two numbers should still be the same. I nucleate it around the point. I drag it all around the manifold, close it on the other side. Here, right? And I close it to the point. And then as I do that, I pick a DJ, as I did before, integrate it over the whole manifold. That picks up the charge of this operator. So these are these faces here. And then this operator closes to the entity and you get nothing. So you get the partition function with insertion of charge operators, you get a phase times the same partition function. Just think here. So since we get to choose alpha, that is how much the group element that we're acting with. It means that these two numbers can only be equal whenever this sum is different from zero, whenever they are both zero. Okay, is that clear? Standard argument. All right. So I want to take this story, which I'm sure is familiar to many of you, and I want to translate all this to the language of SIMTFTs and anomalies, which to my knowledge hadn't been done before. So what I have just said, one way of translating it is under a transformation of U1 axial of, you act with an alpha, a group element alpha, everywhere, the same element. The partition function picks up a phase, which is e to 2 pi alpha times the index. That's, of course, Fujikawa's result. And emission is the one that actually generalizes most easily to the most modern things. One thing I want to note is that in order to conclude that Z is zero, I really need alpha to be constant here. Right? So I want an alpha that satisfies d alpha equal to zero. And it's important because if I do that, my background fields don't change. I really am comparing the partition function at the point with itself. I'm not moving in the space of connections, not moving in the space of background fields, but I'm acting on the partition function. And that allows me to conclude that the partition function at that point is zero. If I start moving in the manifold of connections, then I can pick up a phase, but I don't learn anything. So to illustrate this, if I take a generic alpha, which depends on space in some way, the change is given by this. You get a phase, an anomalous phase, similar expression, but now integrated. But now my background fields have also changed. And then I'm comparing Z with some background fields, with Z with some different background fields. Those two things are different numbers. Yeah. Okay. I cannot conclude anything. It's important I stay where I am. So I'm making these kind of boring transformations in which the background fields don't change, but I still pick up a phase. So for a lack of a better name, you could call these global transformations, but this I think is confusing because we are talking about global symmetries. We are calling these rigid transformations. They're a bit like a gauge transformation, but the gauge parameter is a constant. It seems like we're doing almost nothing. It's actually super useful, as you will see. Okay. So how do we represent these rigid transformations in terms of topological operators? In this language that Miriam, for example, was reviewing just now. So consider the operator that generates the symmetry, this one here. We always write it as integral, so exponential of 2 pi alpha, integral of the conserved current. That's the kind of thing we write for generating symmetries. I'm going to do something funny now. I'm going to choose some theta, assuming that theta exists, such that the boundary of theta is sigma. And I'm going to think of these operators here instead. I'm basically applying a stock, right? So I can integrate d of j over theta. So what this operator does, is whichever operator is unfortunate or fortunate enough to be on theta picks up a phase because of the modified word identity. Anywhere that I don't have an operator, dj is equal to 0, so this operator is just identity. So it's a way of writing something that generates this word, the Takahashi identities. Okay, so if I want to act on my whole manifold, alpha, which is a constant, so every operator picks out the same phase with my action, what I do is choose my theta to be my whole manifold. So the rigid operator is the integral of this divergence of the conserved current over the whole manifold. Now, it might sound a little bit funny, divergence of conserved current integrated over manifold, but the point here is that I have the modified word Takahashi identity, so this is not going to be trivial when I have operator insertions. This is what I'm calling, in the language of symmetries of topological operators, a rigid operator. So this is almost what we need. But I want to formulate things in terms of the anomaly theory. So this was reviewed in Matilda's talk and in Miguel's talk. Miriam also talked about this, and Link's talk was also very nice, so I have included also. So it has been reviewed already a few times in the conference. So if we have this free fermion in 4 dimensions, just to give a concrete example, the anomaly theory can be written as some Chern-Simons theory of this type. So the axial current, and then something that depends on the curvature and the vector current. So this is the kind of thing I have in mind, a 5-dimensional theory that gives me the anomaly of my theory. And I like to think of this in terms of the SIMTFT. So forget about the left for a second, the left of the pink line for a second. So you have the SIMTFT that realizes your theory, in this case, the theory of free fermion. You have the symmetry theory for the U1s that you have. Yeah, so some sort of BF theories. And I'm introducing this rigid symmetry generator in here that I just constructed for you. Now, I really want to talk about anomalies. So what I do is glue, Matilda discussed this in her talk. You glue an anomaly theory in such a way that any phase that you get from doing a gauge transformation here, you undo with the phase that you get from the anomaly theory. So you do sort of a mirror action on the anomaly theory every time you do a gauge transformation, including one of these almost silly rigid gauge transformations. So what do these ones do actually? So they are the integrals of the conserved current, dj. And in the SIMTFT language, what you have is that the SIMTFT is a BF theory of this type. Here, A can be identified with the gauging of the one form, sorry, of the symmetry that you're talking about, and B is a dual field that you can think of roughly as a gauging of the current. So dj maps to dB essentially in the SIMTFT language. So putting an operator which is integral over this manifold of dj is the same, pushes to the SIMTFT to be an integral over this manifold of dB. That's the thing you should keep in mind. Okay, that's the modification of the SIMTFT is an integral of dB over this manifold. Of course, if you're integrating dB over a manifold, that's the same thing as shifting A by delta function. Right? If you imagine the path integral, I have integral of A dB plus integral over delta wedge dB. That's the same thing as taking A plus delta. So this thing I just said, you have integral of dB, which is the thing that generates the rigid transformation, because the action includes a term which is A dB. You Poincare dualize theta to delta theta, and then you have this term which is dB wedge Poincare dual of theta, and what you're doing effectively shifting A. This is a step, I think, which was new. Now we can represent these rigid transformations in terms of the path integral, the SIMTFT, by doing this shifting of the background fields. Let's test that what I'm saying is sensible. If I now go to the anomaly theory bit, so I should do the same thing, the same gauge transformation. So I'm going to shift A again by this alpha, the parameter times delta. There should be an alpha in here, I believe. And okay, let's do that. So you look at the action of the anomaly theory and you see how it shifts under this change. Well, you obtain the same one as before, this anomaly, and then you integrate this delta theta. Now delta theta, if you look at what's happening here, you have a normal direction and theta is localized in this normal direction. So integrating delta theta over the normal direction will localize you to M4, beautiful manifold. Okay, so you get, you integrate over these 5 dimensions. I split that as an integral over the transverse dimension where the delta lives, and then there's a remaining M4 integral. So this is what I'm seeing here. So I pick up an alpha from this integral. The delta converts the integral over the 5-dimensional space to an integral over the 5-dimensional slice on which the rigid operator lives, and then you're left with the rest of the anomaly theory, which is this expression here, in this case, the index. So I have reproduced from this rigid insertion of rigid operators the anomalous shift of the partition function. Okay. So now this is super concrete and super computable. What do you do? Well, you think of these rigid transformations, which are Poincare duals to cycles in your spatial slice. Could be the whole space if you have a zero form symmetry. Could be something higher codimension if you have a higher form symmetry. And then you evaluate the anomaly theory in the presence of these rigid transformations. So here's an example. You have alpha times delta. This is flat, so I can replace it by any other flat connection. This is perhaps a more convenient one, but doesn't really matter. And then the vector field that I have, I pull back from the slice to where it lives to the whole anomaly theory. So I just translate, thank you. I just translate or pull back the whole field in here, the whole background field. So this is what you have. Again, I emphasize this is super concrete. You evaluate the anomaly theory on this background, and if you find that the anomaly theory has a non-zero action on this background, that means that your partition function picks up a phase when you do this rigid transformation, this trivial transformation, and therefore it needs to vanish. All right. I emphasize this does what we want, because very often we know the anomaly theory, but we don't know enough about the field theory. But all you need to know here is the anomaly theory to do this calculation. Okay. So let me sort of argue that this generalizes easily to Maxwell, and then I'm done. So I studied the 4-dimensional case because I was optimistic and thought I could say something about the invertibles. That's not going to happen. No. So I could have done a simpler case, which is d equal to 2. If you have a Dirac fermion d equal to 2, of course, everything works very similarly. You still have an anomaly, you have vanishing whenever you have zero modes, and so on. There's a subtlety in 2 dimensions, which is that you can have a vanishing even if the normal index is different from 0. There's a mod 2 index in 2 dimensions, but in the paper we explain also that this also follows from more complicated versions of what I'm saying. But let me not do that. Let me instead bosonize the problem. So if I'm in 2 dimensions with a Dirac fermion, I can bosonize. And then what I have is a periodic scalar that has 2 U1s again, but now we typically call them momentum and winding. And they also have a mixed anomaly between them. So you have the periodic scalar and you couple it to a momentum, say, background. This is what you have. You have a one-form symmetry, and it couples in this way to the action. So the vanishing that I found before of the partition function because of zero modes when I have vector current, in this case gets translated to the fact that if the class of, so if AP is a connection of a non-trivial bundle, then this partition function, the partition function comes from this action, should vanish. And this is already much more exotic. It's not obvious looking at this that the partition function should vanish here. From the fermion we're used to, right? You have a zero mode, this thing should vanish, but why should this vanish? In fact, it's not that easy even to speak out of this because d phi here is a trivial connection, is d of some connection, so as a connection is trivial. Well, this thing I'm saying, well, choose it to be non-trivial, so what I'm really saying, typically in action you should have form, wedge form. If anybody's interested, I can explain that. There's a way of doing this, but I don't have time. But anyway, this is the problem that Sieta, Chikao, and Yonekura were worried about. And they give a number of reasons why they say, well, fine, maybe this action is not super sensible to write like this. Again, I stress there are ways, I think, to write the action. But let's try to give it a meaning. And the only meaning you can give it in a sensible way is that the theory, whenever AP is different from 0, I mean, a connection on a trivial bundle, should have a vanishing partition function. And here are some answers they give. So reasons they give for this. I just told you, if you start with formalization, this is what must happen, right? The dual fermion has a vanishing. This is supposed to be the same theory in different variables, so better be that this one vanishes. T-duality also requires this to vanish. If you T-dualize, this coupling to the momentum becomes a coupling to winding, which appears in 2 dimensions in this way. In this theory, this theta, this dual, so phi tilde appears as a Lagrange multiplier, essentially. Again, I'm being a bit quick here, but I'm happy to explain details later. So this is essentially a Lagrange multiplier that tells you that DAP has to be 0. If it isn't, the Lagrange multiplier will kill the integral. Because you're integrating over this is fine. Thank you. And the other one is anomalies. They also say anomalies force the partition function to vanish due to the non-zero induced charge argument I reviewed before. This thing that if you have a background, which is anomalous, you have a charge, and in the presence of charge, the partition function should vanish. But you could also do the thing with rigid transformation, and you get the same answer. So we'll finish with Maxwell. The periodic scalar generalizes very nicely to Maxwell in 4 dimensions. In fact, any P-form in any number of dimensions. This is the action that you get for Maxwell coupled to electric backgrounds and magnetic backgrounds. There's a mixed anomaly as before. And rigid transformations, in this case, because they are higher form symmetries, in this case, one-form symmetries, are restricted to 3 cycles now, one codimension 1, over which we integrate dF with F equal to dA. And I didn't go stupid here. I mean, I know d squared is equal to 0, but not quite here, because effectively what you do when you are treating these backgrounds is introduce monopole charge. So you are trying to construct a perturbative theory in the presence of monopole charge. That's why it's so hard to write a Lagrangian for this, but that's intuitively what's happening. Okay, so you have a 3-cycle, you have a Poincare dual, which is pi1. Now you can start mapping torus, you can start the rigid transformation. The only new bit here is that I have to wedge by the class of the object. Before it was a delta of the 4-manifold itself. Now is a delta of the 4-manifold in 5 dimensions, which involves a leg along the transverse direction and a leg on the 4-manifold itself. Okay. And this is, again, a rigid U1 transformation with parameter alpha. So the generalization to one forms of rigid transformations. This is less obvious. The one was obvious maybe, but this one is, to me at least, less obvious. And if you do that, well, you do the integrals, you find this phase. So for the partition of Maxwell not to vanish, you need that this phase is always 1 for any choice of alpha and pi1. And that means that D of B has to be 0 in cohomology. So this is the free-Witten cancellation condition in the simplified setting, which I forgot out the fermions. But as you see, this is super concrete. It follows immediately from the anomaly theory, which is well. So here's a summary of other things we did in the paper. I don't have time to discuss them, but that's fine. So we did do the actual free-Witten anomaly, including the fermions, and you get the answer you expect. You can start stacking branes, and then you have SUN or UN, and there's some subtleties that Kapustin discussed originally, so we reproduce those. You can study anomaly theories, which are of discrete type. For example, discrete Chern-Simons-like theories with group Zn, they're called Digraph-Witten theories, so we did that. We did the original problem that we're after, branes on S-folds. It was not very hard to do M5, so we do free-Witten for M5s. Again, always the same argument. If you do anomaly theory, and we do, for M5s, you can understand the free-Witten anomaly. We did the 2D mod 2 indices that I was talking about. And the thing I was going to discuss, but not going to discuss, is some 3D minimal TFTs appear in the context of non-invertible theories. Okay. So I'm just going to conclude. If anybody's curious about non-invertibles, let me know, because I think that's an interesting story. So this is, as I try to emphasize, really hands-on, something you can sit down and compute. There's no path integral over wall sheets or anything complicated you need to do. It's fairly accessible, I think, if you know the anomaly theory. So there's a couple of directions that I think are interesting, probably more, but a couple of them we're thinking about. Oh, sorry, we have discussed at least. I did basically everything for ordinary higher form symmetries, but of course there's a question what happens with more general categorical symmetries. I'm sure there's interesting stuff there. And there's also this really nice paper by Shani and collaborators, where they discuss a vanishing that I think can be explained also using our techniques. So it will be interesting to look into that. So basically a non-abelian version of what we think.
Thank you, Iñaki. We have time for a couple of quick questions.
Okay, thank you. So in your calculation, it was very important that the manifold is compact, right?
Closed, yeah.
Yeah. Do you have any intuition what happens if it's a non-compact manifold, how the boundary conditions at infinity can carry charge and maybe do something funny in this?
Yeah, I think they will alter the discussion significantly, because typically what happens if you do a gauge transformation, it can act, right, compact manifold, and then you cannot compare the same thing, right? You're moving a space of things, and then you may have a holonomy, but that doesn't allow you to conclude anything. Yeah, so basically there's less information in that case. I'm not saying that there's nothing interesting to say, but there's definitely more subtle, because you have to worry about not moving the boundary conditions of infinity to learn anything. Yeah.
Hi, Iñaki. Thanks for the nice talk. So just to understand clearly the rigid transformation in the SIM-TFT setup, so is that a topological operator in the SIM-TFT?
Yeah.
So then, again, passing the question that Jonathan asked to me now to you, that would define some sort of a -1 form symmetry. Is that correct?
Yeah. I suppose if I'm being strict on definitions, yes, but it comes clearly from doing some.
But then it looks like something like the 't Hooft anomaly that's now been shifted by this, right? That's what's been shifted, and you sort of think 't Hooft anomaly as like a parameter that's the -1 form symmetry charge, and okay. I just
it's not. I mean, for example, this case of the Dirac fermion, you could understand this way because you're shifting the action. Essentially, that's what happens in the end, right? For higher form symmetries, I don't quite know how to speak in that language. I suppose you can.
Okay, very last question.
Thanks for a very nice talk. I wanted to ask if you had a list of examples. Have you thought about the Diaconescu-Moore-Witte and the W7 = 0 obstruction?
Oh yeah, good one. Yeah, we thought a little bit about that. When we thought about the M5, we did find generalizations on the standard flux condition G4 plus lambda halves, whatever. The answer is yes, we have thought about this. I don't think I have anything sharp to say about W7 at the moment. But yeah, it's in the radar.
Okay, so now we have the break. We reconvene at 3:30, but first let's thank Iñaki again. All right, hello again. It's a pleasure to start the second part of the afternoon session with Ichil Kim discussing 6D supergravity blocks, please.
Okay, first of all, I'd like to thank the organizers for putting together this wonderful conference and also giving me this opportunity to present my work here. So today I'll be talking about supergravity blocks. This is based on my ongoing work with Yuta Hamada at KK and also Sungmin Jeon at Poste. Okay, let me begin with the motivation. So now it's widely believed that the landscape of consistent quantum gravity is finite, whereas the swampland of EFTs without UV completion is vast. This is a finiteness conjecture, which was indeed discussed in several talks in this conference. Today, I'll be talking about 6D10 supergravity. I believe this class of theories is a perfect testing ground for this finiteness conjecture and also related ideas for the following reasons. Firstly, they are highly constrained. So the anomaly cancellations, symmetry, together with the unitarity impose tighter restrictions on the structure of the effective field theory. And second, they have rich non-perturbative structures such as tensionless VPS strings, fixed SCFTs, and little string theories. And quite surprisingly, all these objects are classified. So we can test our ideas against their classifications. And thirdly, the finiteness of 6D supergravity is partly proven in my recent paper with Kumnun and Kai-Su. We actually proved the entire massless spectrum is finite. And lastly, there is a beautiful connection to F theory and also geometry. So this class of theories are interesting and very important. Okay, let me briefly give you some the new ideas which we discovered in our recent paper. So we start with two assumptions. The first assumption is that every boundary of the tensor moduli space in 6 dimensions hosts tensionless BPS strings. And second assumption is the classifications of 6 SCFT and little string theories are complete. And all the known string theory constructions satisfy these two assumptions, by the way. Then based on these two assumptions, we can actually obtain the following result. Firstly, BPS string charge cone, which we just call the BPS cone, is dual to tensor cone, and it's generated by primitive BPS string charges, which are related to the tensionless BPS strings. And secondly, and more importantly, we actually prove the existence of a universal BPS strings, which we call H string because it's related to the critical heterotic string. And quite interestingly, it turns out that the existence of this H string provide very, very strong constraint on the 6D bulk effective field theory. For example, using these ideas, we can prove the number of massless spectra in any 6D supergravity is finite. More precisely, number of tensor is bounded by 193, and total rank of gauge algebra is bounded by 480. Then together, it implies that consistent EFT landscape is a finite set, and they are actually classifiable. Okay, this naturally raises the following questions. So can we systematically construct all 6D supergravity theories? And can we classify all of them? For this, today, I propose a bottom-up construction framework for 6D supergravity theory. The basic idea is to build any supergravity theory from a finite set of basic units, which we call supergravity blocks. By the way, we couldn't find a better name, so we just put the name as a supergravity block. Using these blocks, we can systematically construct any supergravity theories as a Lego game. Okay. And for the classification, I provide a complete classification of non-Higgsable supergravity blocks, which will become the basic building blocks in this framework. Okay, outline is the following. So I'll first give you the review on 6D supergravity, then I'll explain the refined structure of the tensor moduli space, which we discovered in our recent paper with Kumnun, and explain the role of the H string there. Then I'll introduce our construction framework for the 6D supergravity and give you the definition of the supergravity blocks. And lastly, I'll present the classification result for the non-Higgsable supergravity blocks. Okay, let me begin with the review on the 6D supergravity. So there are 4 types of massless supermultiplets. First one is, of course, gravity multiplet. And there are also T-tensor multiplets, each containing anti-self-dual two-form field and real scalar field. By the way, the scalar field parameterize the moduli space called the tensor moduli space. There are also V-vector multiplets for the gauge algebra and H hypermultiplet for the methods. These multiplets contain the chiral methods, so they provide chiral, gauge, and gravitational anomalies. Such anomalies can be cancelled in 6 dimensions using Green-Schwarz Segnotti mechanism, but this mechanism requires the following conditions. It looks complicated, but it basically provides very strong constraints on the types of methods, such as gauge algebra, charges, and shape of the tensor moduli space. The first constraint comes from the gravitational anomaly cancellation, and rest are from the gauge anomaly cancellation. In this anomaly cancellation condition, we have vectors B0 and Bi, which we call anomaly vectors. They are living in the tensor charge lattice. Then together with the tensor intersection form omega, they determine the structure of the tensor base. Okay, let me explain the tensor moduli space. It's p-dimensional coset space parameterized by scalar J in the tensor multiplet. And on the tensor moduli space, we have famous BPS object called BPS strings, and their tension can be easily computed. It's proportional to J dot Q, where J is the moduli and Q is the tensor charge. Then unitarity requires that this combination must be non-negative. So string tension must be non-negative on the moduli space. So tensor moduli space should satisfy this constraint. And as we assumed, every boundary point on the tensor moduli space, we have the tensionless BPS strings. Then together, it implies that BPS cone, which is simply cone of the BPS string charge, is dual to tensor cone. And furthermore, this cone is spanned by generators Ci with negative self-intersection, and two generators must intersect non-negatively. And furthermore, we can draw the conclusion that BPS strings associated to each generator can become tensionless somewhere in the tensor moduli space. So these strings are shrinkable somewhere in the tensor moduli space. So this figure give you the schematic structure of the tensor cone, which is the cone of the tensor moduli space, and also BPS cone. Okay, so as I said, all the strings associated to the BPS cone generators has tensionless limit somewhere in the tensor moduli space. So they are shrinkable, and they are all classified in this paper, which discuss the classifications of 6 SCFTs and little string theories. So it turns out the BPS strings fall into the following 2 classes. The first class is instantonic strings. They are basically instantons for the gauge algebras. And this table summarizes the types of such generators. So here we have allowed gauge algebra for instantons and charged metals, and their intersection properties are specified here. So as you see, the structure of the BPS generators is very constrained. Furthermore, there are more generators without gauge algebras. We have 4 of them, E string, M string, they are very famous, and we also have H string and type 2 string. And as the name suggested, they are related to the heterotic string, critical heterotic string, and type 2 string. Indeed, these 2 strings have tensionless limit at infinite distance. Then these 4 generators, together with the instantonic strings, form the complete set of primitive BPS generators for the BPS cone. And they are classified. The image, we can extract the very concrete structure of the BPS cone out of this information, therefore the structure of the tensor moduli space. And from that information, we extracted the very refined structure of the tensor moduli space. The key statement in my paper with Kumnon is the following. First, intersection structure of the tensor moduli space must match that of the Kähler surface, P2 or Fn or their blobs, except B0 scale equal Z case. And furthermore, we can prove the existence of H string in every consistent quantum gravity theory in 6 dimensions, preserving H for charges. And H string is defined with the charge F scale is 0, and F dot B0 equal to 2. And this property implies that H string is essentially the critical heterotic string. And this argument is, by the way, purely field theory statement without assuming any geometric embedding. Okay? And this basically implies that we can take the sequential blowdowns, which is just projection in the BPS cone, removing the -1 generators. Then after such a sequential blowdowns, the tensor cone must terminate a cone of the Hertzsprung surface Fn. Okay? And this implies that any supergravity base for the tensor multiplier is given by blob of P2 or Hertzsprung surface Fn. So topology of the tensor moduli space is basically geometry. So this is a very non-trivial realization of the string Lampos principle for the tensor structure of 6D supergravity, not the full gravity or structure of the full gravity, but the tensor structure is really geometry, can be realized in string theory. And consequence is that we can systematically now enumerate all allowed tensor bases by simply blowing up point of Hertzsprung surface Fn. And this enumeration actually becomes the finite problem, and they are classifiable. Okay, as I said, we always have H string in any 6D supergravity theory. And that existence of H string provides the following constraint. Firstly, we have the bound on the rank of gauge algebra sitting on the external generators. So generator fall into 2 classes. One is external, if it positively intersect H string charge F. And all the other generators are orthogonal to the H string. When they intersect positively, we call them as external generator. In this case, the gauge algebra sitting on this external generator actually provide current algebra on the world safety of H string. Then the unitarity of this world safety enforces the following rank bound. So the total rank of the gauge algebra sitting on the external generator is bounded by 20 or 16 when number of tensor is greater than 1. And all the other generators are orthogonal to the H string charge. In this case, we have containment relation. Such orthogonal generators must be contained in a little string theory, whose little string share the same charge F as the critical string. So we have this containment relation. Then this containment relations tells us that we can now use classifications of the little string theory to extract non-trivial structure of these orthogonal generators. Okay, so the generators which are orthogonal to H string charge F are very strongly constrained from the little string theory classification. And thirdly, it turns out that the little string theories sharing the charge F always have p-type endpoint. And this class of little string theories are very simple, relatively simple, and very interesting. They don't allow circular intersection, firstly, and secondly, they don't include any frozen singularity. So this type of little string theories are simple. And together with tensor and V-bound, actually the allowed little string theories with p-type endpoint form a finite set, and they are also classifiable. And they become backbone of the any Shikti supergravity theory. Okay, this constraint tells us the following very beautiful structure of the tensor multiplet in the Shikti gravity theory. So we found the tensor intersection from omega must show the following block structure. So it's formed by collection of diagonal blocks. So as I said, generators belong to two sets. One is external generator. The other ones are the orthogonal generators. And orthogonal generators must belong to one of the little string theory sharing charge F. So each block is corresponded to the little string theory A, B, and C, and they share the charge class F. They contain the generators, which is orthogonal to H string. The remaining blocks are external generators. So we have this diagonal block structure, but the mutual intersections between the generators belonging to two distinct little string theories, they don't talk each other. So these off-diagonal blocks are zero. The only non-zero off-diagonal blocks are here, which describe the intersection between external generator and these orthogonal generators. So our tensor multiplet must have this nice intersection structure. After getting this tensor intersection form, the remaining thing we should do to construct the Shikti supergravity is to put the gauge algebras and charged methods on the tensor multiplet. For this, we can use the following information. Firstly, the gauge algebras on the BPS generators, which have negative self-intersection, are all classified. So for such gauge algebras, we know how to put the gauge algebras on each tensor multiplet. However, the gauge algebras sitting on the tensor multiplet with positive self-intersection are not classified. So it's an open problem. Okay. So today, I'll not talk about this. I'll focus on the construction of this tensor intersection form for the gravity theory and their gauge algebras. Okay, now it's time to define our basic building blocks in our framework. So it's called the supergravity blocks. And supergravity blocks is a collection of one block for the single little string theory together with all external generators. So in this figure, this 4x4 matrix form a supergravity block, and another 4x4 matrix come from this 3x3 and off-diagonal component here and here between the external generator and the orthogonal generators. These are supergravity blocks. Then the defining feature of this block is that each block, its gram matrix has exactly one positive eigenvalue and rest are negative. What this means is essentially BPS strings embedded inside each supergravity block cannot become simultaneously tensionless, okay? And furthermore, this implies that every supergravity block contains intrinsic gravitational tensors. So this is the distinguished feature of this supergravity block from other blocks. For example, you can take some block which correspond to local Shikti. They can be simultaneously shrinkable, but this supergravity block, no, okay? So they are basic building blocks, therefore, for the supergravity. Then now let me explain how to build supergravity theory from these blocks. It's very simple. So we just take the supergravity blocks sharing the same external generators and put them together, okay? So then it will construct the tensor structure of a single supergravity theory. Then after getting this tensor structure, the only remaining thing we need to check is the following. So after assembly and sequence of load downs, the intersection form must reduce that of a Herzog surface Fn, okay? So this is the constraint we need to put after constructing these blocks out of the supergravity blocks. By the way, the one important feature is that all the complication coming from gauge anomaly cancellation is already taken into account when you construct the supergravity blocks. So once we have already the classification of the supergravity blocks, then the remaining thing to construct the supergravity is just simple Lego game. We just put them together to construct such supergravity theory. We have one more step. After this, we can place the gauge algebras and charged methods on the positive self-intersection tensors. But since this is not classified yet, I will not talk about. And then resulting theory will satisfy all known consistency conditions. However, that doesn't guarantee the existence of UV completion because we don't know concrete constraint or criterion to distinguish whether the theory really has a UV completion or not at this moment. Okay, so the resulting supergravity theory is not yet guaranteed to have UV completion. So this is one caveat of our systematic construction method. Okay, let me give you two concrete examples from F theory. The first example is very simple. It contains the two tensors, and the F theory base is simply Fn, Hertzberg surface Fn with one block point. In this case, on the tensor cone or BPS cone, we have three generators here. So intersection form is simply given by 3x3 matrix containing 2x2 submatrix for this little string theory formed by two intersecting -1 curve. And there is a single external generator, -n, hosting the minimal gauge algebra. So this intersection form provides concrete gravitational theory formed from the F theory computation. So this omega, the intersection form in this example, contains just a single supergravity block. So this actually tells us that gravity block itself can become supergravity theory. Second example is more non-trivial. It contains 17 tensor multipliers, and the base is given by T4 mod G2 times G2, and this is the diagram showing the generators and how they intersected together for this supergravity theory. Here we have 4 copies of the same little string theories formed by 4 -1 curves intersecting -4 curve. They are glued together through 4 -4 curves here. They are external generators. So for each little string theory, we can construct the supergravity block in this way, which is a 9x9 matrix containing 5 times 5 little string theory sector and 4 external generators. Since we have 4 little string theories in this theory, we just combine 4 copies of the same supergravity block together. Okay, so this construction was discussed in this paper with Kumner again. But this is just an example. Our framework doesn't rely on any F theory assumption. Okay, it's really bottom-up construction. For the classification, I focus on a special subclass, which we call non-Higgsable supergravity blocks, which are built entirely from non-Higgsable clusters. Non-Higgsable clusters are, as you all very well know, so the tensor multiplier configuration whose gauge algebras cannot be further Higgsed. And furthermore, these are actually all classified. So this table shows the classification of NHCs. So we have 12 non-Higgsable clusters from geometry. And furthermore, we have 3 more non-Higgsable clusters realized with frozen singularity. So they are non-geometric. So using these blocks, or using this table, we can construct the non-Higgsable supergravity blocks. Okay. So the reason why we consider this subclass is they are simple, and it cleanly separates the topology of the tensor base from the complication arising from gauge enhancement and the charged methods. And furthermore, once we have a classification of these non-Higgsable supergravity blocks, we can construct the more general blocks by simply enhancing the gauge algebra. So these non-Higgsable supergravity blocks really become the basic building blocks for every shifty supergravity. Then let me give you our classification result. We can first classify all allowed p-type little string theories for the H string, but including only non-Higgsable clusters. So these are the distribution of the number of non-excitable p-type little string theories, and with respect to the number of tensor multiplets. And in total, we found only about 19,000 distinct p-type little string theories. So we can construct out of this data supergravity blocks. And this is the list of the little string theories when number of tensor is small. But the full set can be found on the GitHub. We'll upload this data on the GitHub too. And we finished also the classification of all the non-excitable supergravity blocks. There are only 276 patterns of external generators. And for each pattern, we can construct more than one non-excitable supergravity blocks. But in total, we discovered around 160,000 non-excitable supergravity blocks. And this table shows the patterns, including E8 and E7 external tensors and number of non-excitable supergravity blocks like that. But it's not important. Our full data will be uploaded on the GitHub. Okay. Furthermore, our framework allows us to actually enumerate all possible tensor bases. So we classified or allowed the tensor bases actually up to t equal 10 case. And this table shows our classification up to t equal 6. And this is a bottom-up construction, but quite surprisingly, this result precisely agrees with the geometric tensor base classification by Inan. So they agree. And this output actually shows that the result grows very rapidly as you increase the number of tensors. So it becomes complicated, but the result is, so number of such base is finite and algorithmic. So in principle, we can carry out the classification of the all allowed tensor bases systematically, even for large T. Okay, before closing this talk, let me highlight one novel discovery which we use our construction framework. So we can systematically also construct the supergravity theories, including the frozen singularity. And this theories actually involve the non-excitable clusters with frozen singularity. There are 3 of them. And let me give you 2 examples. First example occurs at t equal 10. Here, this supergravity theory included this first type of non-excitable cluster with frozen singularity. And tensor base is geometric. It's just 10 block point or P2. And this geometric base has a canonical class. Now with t equal 10, this canonical class becomes genus 1 curve with the self-intersection -1. There we can put the SU8 gauge algebra with one symmetric method that is realized with frozen singularity. So this is our final configuration for the gravity theory, okay? But it's non-geometric because it includes the non-geometric, non-excitable cluster. The second example is at t equal 11. This supergravity theory contains another non-excitable cluster, and this is the final configuration for this supergravity theory. But it's again non-geometric because the base now involves the tangential intersection, and it cannot be realized in F theory. But so we constructed these 2 examples, but it's not guaranteed that these 2 examples has a consistent UV completion. But we believe they are consistent to theory because of the following 2 reasons. First one is all SCFT and little string theory subset of these 2 supergravity theories can be realized in string theory with oriented fold plane. Secondly, to argue that the theory has UV completion, it's very important to say that the BPS strings, in particular instantonic strings, has nice, well-defined moduli space. And for these 2 supergravity theories, any instantonic strings existing in this 2 supergravity theory has a well-known UV completion. So this is why we believe this one exists. But then the remaining question is, can you really construct these theories in string computation, which is open question. Okay, because time is up, let me just present my conclusion here. Thank you very much.
Thank you, Ichil. Let's see, we have a few questions.
Beautiful work and talk. Thanks, Ichiro. Do you know with this block method of supergravity blocks, can you get the bounds that we had with you and with Kai?
Actually, here in this program, because of time limit, we put that bound in this program, but I think we can do the other way.
Yeah.
So I'm thinking of doing it. Yeah. Thank you.
Yeah, so I wonder for the t equals 9 case, which is blow up of 9 points on the P2. Then in generally speaking, there are infinitely many -1 curve on the base. So are they allowed in your block classification or no?
Oh no, so here block is like we just, so even for deFreitas 9 base, we can actually consider what is it, H string in the configuration.
Yeah, sure.
For the given H, so our block is first choosing H string class, then construct the little string series corresponding to this H string and build the supergravity block. In this case, so we are choosing one particular basis of this among these infinitely many generators.
Okay.
So that we have finite choices. So we have only finite number of supergravity blocks even in the construction,
but
because we are choosing particular bases.
You think the base is allowed?
Yeah.
I see. Thanks.
I have maybe one last quick question.
I was wondering, could you give a bit of the flavor for how you go about proving, without using geometry, that all of these theories blow down to one of the Hirzebruch surfaces?
Oh, okay, very good. Can I go back? So you're asking this one. It's a bit technical, but one thing, so what we can say that firstly, we should say that on the tensor moduli space, the infinite distance point corresponding to H string is polyhedral. If you can show it, then using, so if it's polyhedral, then this charge F scale is 0. So if it's polyhedral, it must be inside or it should touch the round cone in the tensor moduli space or tensor cone. It means this charge F cannot be generated if T is, after blowing down, if T is greater than 1. It can become generator only when T equal 1. So it should blow down all the way to T equal 1 example, which corresponds to the Hirzebruch surface Fn. Yeah. I can explain more detail later.
Maybe we can get a super last and super quick question.
Hi, thank you for the great talk. So for little strings, we have observed that they sometimes they have this higher two group for symmetry.
Yeah.
And in supergravity, I would expect that the structure constants of these higher groups should all vanish based on examples. But I don't have an argument. Maybe we can discuss it. But does this give you an extra constraint on the supergravity blocks?
I believe so, but I haven't thought about it actually. But it's a very good point. So here I just discussed about just zero form symmetries and everything in zero form. But so considering more higher forms and higher group structure would be providing more constraint. Yeah, that is our hope. So it's a very good point. Thank you.
Okay, so we can thank Ichiro again. Thank you.
Is there? Sounds good. Yes.
Okay, and as the last talk of the session of today, we're very happy to have Jakob Moritz discussing combinatorial F theory uplifts.
Yeah, thank you very much for the invitation. And thanks to the organizers for putting together this wonderful conference here in this beautiful place. Never been to Uppsala, and I'm amazed how pretty it is here. The perfect place for this conference. Yes, so sorry for the last minute change of title. I went for something slightly snappier. I would like to. So this project, as you can maybe see from the title slide, is all about Calabi-Yau compactifications, motivated by studying the string landscape in detail. I'm going to jump into essentially using combinatorial descriptions of toric geometry to arrive at F-theory uplifts, starting from Calabi-Yau threefold orientifolds in type 2b. Okay, so here's the outline of my talk. I'm going to start motivating a little bit why I'm doing this. Wanting to study the string landscape, specifically flux compactifications, and being able to evaluate the flux superpotential in these potentially phenomenologically interesting compactifications of string theory. I'll then go on to show you how to classify and systematically construct O3, O7 orientifolds specifically in Calabi-Yau hypersurfaces in toric varieties. And then I'll go on to show you what I mean by combinatorial F-theory uplifts, and then I'll conclude. So this is all based on an upcoming work, hopefully in the next few weeks or so, together with my wonderful postdoc, Björn Hasfeldt, who joined us in Madison last fall, and who's been doing almost all of this work. And I want to highlight that he recently changed his name because he got married, and he adopted a new name. He's now Björn Hasfeldt, no longer Björn Friedrich. He wrote a bunch of awesome papers in his PhD, so I want to make sure that everybody knows that these are the same people, and those are not lost in his CV. Yeah, let's get right into it. Okay, so a little bit of motivation. Of course, as you all know, there's huge open problems in particle physics and cosmology. On the one hand, we have the tantalizing hierarchy problems. We have, of course, the electroweak hierarchy problem, why the Higgs mass is so small. We have the famous cosmological constant problem. We have, in addition, small Yukawa interactions. We have small CMB anisotropies, neutrino masses, and of course also the strong CP problem. And we would dearly like to know, can we use string theory to shed new light on these fundamental problems in particle physics and cosmology? On the other hand, we also have the yet unknown nature of dark matter. Of course, so if you look at this, maybe you can see that I'm hoping that maybe axions will be detected, maybe stringy axions. So I think there's a lot of motivation for trying to address these problems here in string theory. But I think so far we have to admit that except for in very simple toy models, we cannot say a whole lot yet about what string theory has to say about these problems. Okay, so why should one use string theory to address these issues? Well, at least the fine-tuning issues in the standard model and Lambda CDM are sort of by definition UV sensitive, involving a cancellation of contributions from loops at very different scales. So I would say it's quite possible that a detailed understanding of the string landscape may shed new light on on how to think about these problems from the perspective of quantum gravity. Since a small cosmological constant or a small Higgs mass the reason we find that unnatural is very much based on from a bottom-up point of view, and it's quite possible that in string theory, actually, once we understand the string landscape in a lot of detail, in addition have solved the measure problem, maybe we will develop a different notion of naturalness. This is at least plausible to me. Okay, so how would one go about this? Well, the string landscape, specifically in 4D n equal to 1 flux compactifications of type 2, type 2b string theory on rentifolds or F-theory compactifications is certainly believed to be extremely vast. So maybe it seems like I'm contradicting Hichiro here, is that the swampland is vast and the landscape is finite. I agree that it's probably finite, but it's still vast. There's, of course, the famous 10 to the 500 from a study by Kutcher et al. About 20 years ago. And there's a much more shocking estimate due to Wally Taylor and Yan Wang of around 10 to the 272,000, I believe, flux vacuum just in a single compactification. So what do we do with this? This is quite dramatic. I would argue, well, obviously we cannot by hand or with pencil and paper just enumerate all of these solutions one by one and see what they give us. But it's quite possible that we can that we will be able to develop tools that allow us to statistically study the landscape of flux compactifications in a way that you can essentially put it on a computer. And maybe then we can work out statistical predictions in the string landscape. And I mean, the vast number that appears here, I think makes it very clear that the way forward for this particular problem is not to study individual flux compactifications with pencil and paper, but develop computational tools that allow us to automatically study the string landscape. Okay, so here's a wonderful tool that has been giving us more and more over the past decades, which is the Butterriff's construction of Calabi threefolds as hypersurfaces and compact Voigt varieties, and the most important ones arising from four-dimensional reflexive polytopes have been classified by Kreutzer and Skarke. So what's the idea? We consider type to be on, well, it doesn't have to be type to be, but we consider hypersurfaces and Voigt varieties. You can just think of generalizations of the elliptic curve here in weighted projective space 231. Sort of standard example, but in these the toric varieties, just the generalizations of weighted projective space 231 here, famously can be constructed in purely combinatorial terms, as shown by Butterriff. So what does one have to do? Well, one picks one of the roughly 500 million reflexive polytopes in 4 dimensions. Here's the 16 reflexive polytopes in 2 dimensions, just as a cartoon. And well, okay, those are already a lot of choices. But then what one has to do is to define a toric variety whose anti-canonical hypersurface is smooth. One has to actually triangulate the faces of these 40 lattice polytopes depicted here. So you can go this way, that way, and so on. And the sort of vacuum degeneracy of these models is dominated not by the number of polytopes, but the number of different triangulations you can choose here. So there's an estimate of, there's an upper bound of 10 to the 296 Calabi threefolds that you can arrive at in this way. It could be much less if there's isomorphisms, accidental isomorphisms between these Calabi, but this is sort of the ballpark that we expect. Okay, so how do we study this in detail? So collaborators of mine have developed the software package COI tools, which allows you, which is sort of a collaborative network where everybody who's interested can contribute algorithms to study these beasts effectively. And so there's a lot of things we can do already. We can study the sort of classical algebraic geometry of these hypersurface Calabi-Yaos, such as the intersection theory, Chern classes, etc. And also we wrote a paper about computing Gopa-Kuma Vafa invariants in these, so we can also do enumerative geometry in these Calabi-Yaos. So if you're interested in studying Calabi-Yao manifolds, I invite you to join these efforts and construct more and more computational capabilities for Calabi-Yao manifolds. So the important upshot here is that Calabi-Yao varieties, as well as their properties, can be encoded in essentially combinatorial data of 4-dimensional reflexive polytopes. And this is an invaluable tool in order for us to be able to study the landscape, not just in simple examples, but really in complicated, topologically complicated examples that we believe to be generic in this 40 and equal to 1 landscape of string theory. Okay, so this is just the purely geometric part. Calabi-Yao compactifications of type 2B string theory, of course, give you 40 n equal to 2 supergravity. So in order to get down to 40 n equal to 1, what we have to do is also to specify a orentifold involution, which in type 2b string theory should be holomorphic. So what does this mean? We choose some holomorphic involution of the Calabi-Yau, which for my purposes, I'm going to assume maps the holomorphic 3 form of the Calabi-Yau to minus itself. And so in this example, it could be something like x comma y goes to x comma minus y. And one has to make sure that the defining polynomial is invariant under this transformation. And then this also defines for us a holomorphic involution of the Calabi-Yau threefold. So here in white, I'm just depicting some fixed locus, which would then be the location of an O7 plane or an O3 plane. Okay, so what do we actually do? We take type 2b string theory and mod out by -1 to the FL, where FL is the space-time fermion number coming from the left movers, worldsheet parity, and this in combination with this geometric involution, and we get 40 n equal to 1 supergravity. So besides these universal parts, what the non-universal part is the holomorphic orentifold involution, some Z2 involution, and I studied this a few years back, so I classified all the different choices you can make for Z2 involutions of 40 toric varieties and what they induce for Calabi-Yau threefolds. So the orentifolds of Calabi-Yau hypersurfaces in toric fourfolds are now in principle fully classified. Okay, so having in hand such involutions is not enough. What we would like to do in order to study the landscape of 40 effective theories is we have to understand how to compute the relevant EFT data. So this involves in particular the complicated real Kähler potential K, which we usually only know at tree level and have so far very little to say beyond. And then we have the holomorphic superpotential, which is of course easier to study because it's holomorphic, and yet we still don't know a whole lot about it beyond the classical expression. And why are these important? Well, of course, one would like to know what the EFT data is, but in particular, the stability of any kind of vacuum you might derive from this data and compatibility with, for instance, absence of fifth forces compels us to find isolated minima of a scalar potential with sufficiently large masses of the moduli, and yet with a small Higgs mass for some reason. So the relevant scalar potential is, well, the F-term potential in 40 n equal to 1 supergravity, of course also be a D-term potential, which of course, and this depends on the superpotential and the Kähler potential. So in order to really understand the vacuum structure of these 40 n equal to 1 effective theories, we actually have to know what K and W are. And in many cases, well, usually, or almost always, the classical expressions are not enough in order to lift the vacuum degeneracy. All right, so we need, for sure, a computation handle on the superpotential as well as the Kähler potential. Okay, let's focus on the superpotential for a second. The classical superpotential, which is exact up to non-perturbative corrections, is the Vafa-Witten superpotential, which I'm going to already write in terms of F theory, in terms of the quantized four-form flux and the holomorphic four-form of an underlying Calabi-Yau fourfold. And I'm going to write it, so the moduli enter here. So first of all, this is an integral over the genus 1 fibered Calabi-Yau fourfold, the so-called F theory uplift. Tau is the exodilaton. Z are the complex structure moduli specifically of the Calabi-Yau threefold, which I'm singling out here, and phi are the D7 brane position moduli. And because these forms are closed, I can write the entire thing just as a linear combination of Calabi-Yau periods. So I have my period vector, which depends on all these moduli and is computable in principle just from the combinatorial data that defines the toric varieties for us. There's a related quantity, which is sort of the threefold version of the Vafa-Witten superpotential, which involves the three-form fluxes in type 2b and the holomorphic three-form of the Calabi-Yau threefold. And this you can think about as the limit of this expression when all the D7 branes sit right on top of O7 planes. So this is something that's in coming up with explicit flux compactifications we've been making use of a lot in recent years, but it's not actually enough for computing the D7 brane moduli masses because they've already been set to 0 here. Sorry, the moduli have already been frozen by hand. So really, even for compactifications that sit right in this weakly coupled type 2b setting, what really would like to know how to go away from this strict Sen limit, if you will, to understand what the mass spectrum of these 7 brane moduli actually is. So not just in order to study generic F theory, but also just in order to understand modular stabilization of weakly coupled type 2b, we really want to understand what the full thing is here, the fourfold Vafa-Witten superpotential. Okay, so what do we need? We need to begin with, we need an algorithm to move back and forth between Calabi-Yau threefold orientifolds in type 2b. There are F-theory uplifts, which are the porous fiber Calabi-Yau threefolds, which, if I from these take the Sen limit, brings me back to my Calabi-Yau threefolds, or their orientifolds. And the upshot of our work is that we found an explicit realization of this map at the level of reflexive polytopes. On this side here, 40 reflexive polytopes. On this side, on 60 reflexive polytopes, and 2 defining equations that give you a Calabi-Yau threefold, Calabi-Yau fourfold, codimension 2 hypersurface. And we're preparing a Python package for CBOY tools that will be published via GitHub, I believe, which will allow everyone to be able to use these to make use out of this dictionary in order to study well, whatever you want. I also want to highlight that at least for a subset of these orientifolds, we find that we get to relatively special 60 reflexive polytopes, which admit a so-called Neff partition. In these cases, mirror symmetry is extremely well understood, not just on this side, but also on this side. And so this gives us an awesome handle on computing the periods of the fourfold. For that, we usually use mirror symmetry in order to really understand all the monodromies. And so I hope that in the near future, we'll be able to use these tools to effectively study the classical superpotential in F theory. All right, so let me model area for on time. Okay, so how do we define Calabi-Yau orientifolds? Well, it turns out that the holomorphic involutions of toric fourfolds V are generated by two maps. One is something that lives just in the algebraic torus, the dense torus inside the defining dense torus inside a toric variety. And so you can think about this as as a map that maps some coordinates to minus themselves. And the inequivalent choices are just elements of Z2 to the 4. So there's just 16 choices you can make. Quite simple. The other part here is induced from symmetries of the toric fan. So this something like x1 goes to x2 and vice versa. But we're not going to consider this latter part here. Okay. So one thing to keep in mind is that in general, in order for this to make sense on the Calabi-Yau threefold hypersurface, I need to make sure that the complex structure moduli of the Calabi-Yau threefold hypersurface are tuned such that the polynomial gets mapped to itself up to some complex phase. And so it has to be projectively invariant under the orientifold involution. So in general, so we cannot assume the generic hypersurface equation in general. So in the most useful way, I think, to think about these is then to view the orientifold itself, which is the Calabi-Yau mod Z2, as a general hypersurface in an orbifold toric variety. So you take the original toric variety and mod out by Z2. And so now you don't have to think about special hypersurfaces anymore. You can just think about line bundle properties of the line bundles on these fourfolds. So since an orbifold of a toric variety of the form that I laid out before is again a toric variety, we again just consider hypersurfaces in toric varieties. Okay, so how does it work? Here's a picture of P2. One way to specify, I mean, the most an invariant way to specify evolutions is you refine the lattice. So you add a point to the lattice that wasn't previously there, and for Z2 evolution has to be half integral. So something like this point here. You shift the lattice by this point, take the union with the original lattice, and you get a finer lattice, which now gives you P2 mod Z2. Of course, then some of the generators might no longer be integral, so you might just want to rescale them to get primitive generators. But essentially, the toric fan just stays the same. The underlying lattice changes, and here you get now weighted projective space 2 on 1. So this is just an example. This works in general for toric varieties. Okay. So far so good. Maybe we have understood how to define Calabi-Yau rentifolds starting from Z2 symmetries of toric varieties. Let's see what we can do about the F3 uplifts. So of course, as Krumman showed us, the relevant fourfold is a torus fibration over base, and the base is precisely the Calabi-Yau rentifold, my B defined as the Calabi-Yau mod Z2. And of course, over a 7-brane, in general, the elliptic fiber will pinch. And from now on, the strategy is relatively simple and has been explored in works by Colinucci a while ago and more recently by Kim and Jefferson. What we do is we first construct a weighted projective space 231 fibration over the base toric variety that I'm calling the tilde 4 here, and this gives us a toric sixfold. And the toric fan of the sixfold is uniquely determined in terms of the fan of my base and requiring that the Weierstrass model makes sense and leads to a Calabi-Yau fourfold. So this you can just do. This is very simple. F and G are global sections of 4 and 6 times the anticanonical of the base, which I'm going to view as a line bundle on this variety here. Okay, so the key technical obstacle here, so this seems relatively straightforward, but in defining our Calabi-Yau rentifold hypersurface, we have started with something that was generically smooth, but now we have tuned moduli. So H21 minus of the rentifold is in general less than H21. In general, it's no longer guaranteed that the hypersurface is smooth. And so this basically threatens the entire construction. An example of how this could happen is I'm showing here. Consider the conifold with a particular Z2 action. The left-hand side gets sent to minus itself. The right-hand side is a constant. It's the deformation parameter. So the orentifold gets rid of this deformation parameter, and we get a singular conifold. We could call this a frozen conifold singularity. There's no way to deform it. So this is kind of a problem, but of course there's a solution, at least after you discard models that are sort of obviously extremely singular, corresponding to reducible varieties, things that are singularities that live at infinite distance. You can basically, the remaining models can be smoothed by an appropriate birational morphism. So in this case, we can just go into the small resolution of the conifold and make the model smooth. And of course, we would like to do this in general, not just on a case-by-case basis. And the way we do this is we want to use these morphisms to get to a place where we can apply Bertini's theorem. Should hurry up to make sure that these varieties are smooth. So one way to do this is you have to demand, or you have to somehow ensure that the line bundles the divisors associated with the line bundles of these polynomials are in the closure of the Kähler cone. And so one way to interpret this is, well, one has to tune the models such that this is the case. Another way to do this is you change the birational geometry of these sixfolds in such a way that it is the case. This is going to be our approach. And we developed a computational algorithm for this, which is in the spirit of Batterer's work from 30 years ago. And it goes as follows. You construct a certain polytope associated to these line bundles, so-called Minkowski sum. You first define a singular toric fan from this for this toric variety, basically by taking the normals over faces of these of this polytope, and then you add blowups systematically. You add all the blowups that are allowed while retaining that the vanishing orders of f and g are less or equal than 2 and 3. which gives you I0 star singularities. That's the most you should get in 07 orientifolds, and without removing any sections of 6 times the anti-canonical. So the Weierstrass model should stay generic. And this then systematically resolves all the singularities like the conifolds that we saw before. Okay, so if you're interested in the details, maybe you can go through the slides and see how this works in detail. I'm completely out of time. So the point is that we can do this systematically. This is a finite problem. So if you refine toric fans, usually you have to worry about that there's infinitely many toric fans, but these requirements of vanishing orders less or equal than 2 and 3 just make it completely finite, and there's a well-defined way to get to the maximally refined toric variety. So there are similar constructions for toric base F-theory bases that have appeared before, but this is a different way to do it. All right, so this doesn't always work. Some models have to be discarded, and let me just show you that this works at large Hodge numbers. So here's an example with H1 equal to 149, H21 equal to 1. We can find the F3 uplift here. There's a bunch of 07 planes, and we can get the physically correct Hodge numbers of the fourfold, and you can just define it in a nice way. Okay, so this works quite generally, and oftentimes you get these wonderful Neff petitions, so where we know mirror symmetry very well. So this is a fairly workable mechanism to pass back and forth between weakly coupled type 2b and F3. Okay, I'm going to just conclude here, and thank you for your attention.
Thank you, Jakob. Do we have any questions?
Thank you for the talk. So are you saying that in all those models, if you start with a standard general F-theory configuration, you can go to a point where you have a Sen limit, so there is no obstruction? Or?
Yes, yeah. So, I mean, okay, one could have said, why don't we just start from just general Cabrio fourfolds and take Sen limits, and then we're done. But these Sen limits that was shown by Helverson and Cody Long are extremely rare. So basically, this is the reason we want to go the other way. We want to start with the orientifolds in type 2b, which we can already classify, and there's many, but not too many, and then construct the F-theory uplift. So then by construction, the Sen limit always exists. But these are very special fourfolds. They have non-hexable clusters that just have SO8 gauge groups.
Okay, got it. Thank you.
Moritz, can I ask? Here. Maybe you said it, I missed it, but is there a way that you can also match flux configurations across this map?
I think so. I mean, basically, this is what we want to do in the future. We want to study the flux superpotential, and then some of the fluxes will correspond to world volume fluxes and 7 branes, and some will be the bulk fluxes. And since we know the fourfold periods and the threefold periods, we can just match.
Thank you. Very nice talk. So in your searches, what's the maximum D3 brane charge that you'll get?
Okay, good. We haven't done any systematic scans. We're still finalizing the details of the construction itself. But we've certainly seen, I mean, relatively simple models such as the one that I showed you before here have Chi-over 24 can be of order 1,000. That can
1,000,
yeah,
1,000.
yeah. I don't think much higher. Yeah.
Any last question? Yes.
So in this future direction, so how do you realize the standard model gauge groups in which type of model?
How do I? Okay, good,
Yeah.
good. Actually, I'm working in a different project with Elijah Sheridan and Federico Compagnini and Jim Helverson on this question. You can there's another, you can find a combinatorial approach also to that problem. Basically, you start with certain polytopes where there is a natural way to put D7 branes in such a way that you get these classic intersecting brane configurations. Yeah, so it's definitely
limit. It's in the sense limit.
Sorry?
Is it still in the sense limit?
Well, finitely, I mean, it's not all the way in the Sen limit. It certainly doesn't arise from SO8. But I mean, you just have literal D7 branes and O7 branes. That's all. So
Like
you
ISO
have
10, like ISO 10 or this kind of models.
no. I mean, you can I mean, the models that we have in mind is where you have you get SU3 or U3 from a brain image brain pair. You get SU2 from an SP1 from an orientative invariant divisor, and then there's another. Yeah. This can be done. This is also why I want to. So these projects are kind of complementary. I want to study the Higgs potential, for instance, in these kind of models using this technique here.
Okay, maybe there's a very last question from Miriam.
Fractions of globally consistent standard models F theory, right, have been done, and these examples, quadrillion of them that we found, have typically a relatively small number of D3 branes. So it's somehow worrisome, right, that with fluxes you may overshoot.
Yes, absolutely. So this is something where Elijah has developed awesome technology to sort of minimize, to find flux configuration for which you minimize the D3 charge. And yeah, often you get quite large D3 charges and then you're done. You can't do it. Yeah.
Okay. So as far as I recall, there's no announcements to be made. So apart from, of course, wishing you a nice evening, and of course, we should thank Jakob again.
Thank you.